Hey, this is Andrew Brown bringing you another free certification course, and this time it's the NVIDIA-Certified Associate AI Infrastructure and Operations, also known as the NCA AIIO. And the way we are going to obtain certification is by going through the lecture content, doing hands-on lab, and as always, I provide you a free practice exam. And the idea here is you'll get that certification, put on your resume, your LinkedIn, and try to go get that NVIDIA job you've been looking for, as they're super popular right now. I just want to remind folks that if you like these kind of certification courses and you want to see more of them, the best way is to support the additional optional paid materials over at exampro.co. That's going to get you access to more practice exams, cheat sheets, layered content, flashcards, and more. But if you don't know me, I've taught a lot of courses, certification courses here. That includes AWS, Azure, GCP, Terraform, DevOps, AI courses, Kubernetes, you name it, I've taught it. But with that out of the way, let's jump into the course and have a fun time, okay? Hey folks, we are at the start of our journey asking the most important question first, which is what is the NCA AIIO? So that stands for the NVIDIA Certified Associate AI Infrastructure and Operations exam, and it's an entry-level certification that helps you understand the NVIDIA hardware for data centers, the management tools to manage said data centers, and specifically the DGX ecosystem. That is the product that you're putting in your data centers to get that AI capabilities. The course code here is NCA AIIO. Who's the certification for? Well, consider it if you are looking to adopt NVIDIA infrastructure for your organizations. So if you're working in pre-sales, or you are a solution architect or something, this might be the course for you. If you just want to know what it takes to actually run LLMs with the actual hardware for enterprises, even if you don't plan on using NVIDIA hardware, but there's not really many other options, this really helps put in perspective power usage, and like heating and like what kind of models you can run, things like that. Or you just want to become familiar with the NVIDIA hardware. That was my main reason, was that I just want to deepen my knowledge on the AI hardware side. I already had gone to other providers, and so NVIDIA was on my bucket list to do. So we have the associate track, and the associate is more like a fundamentals track because they don't have a fundamentals or foundation. And so this is the one we're looking at. So the top track here is going to be about infrastructure. The bottom here is going to be more about developer or concepts. And so the associates go into the pros. And these pros are expensive. I believe they're like $400 per certification. And also you'll have a really hard time applying that knowledge because most folks that are doing the pros are probably partnered vendors and have the actual hardware, whereas you'd have to conceptually learn it. I do believe that at the time of this video that there is a niche to be made by learning NVIDIA infrastructure. And even if you conceptually learn it, you'll be heads over everybody else on it because, again, it comes down to access to this hardware and not many people have it. So there's not a lot of experts in this stuff. But I mean, if you just want to conceptually get the knowledge you need, I think that the NCA AIIO is great. The Gen L and Gen M, they're okay, but I mean, it's just generic, well, not generic, but it's just general AI concepts, but with an NVIDIA twist. And I think there's better resources out there like my Gen AI Essentials, which is agnostic, okay? And so there are many different professionals for the developer track, but you're seeing those are very specific things. Like you'll see accelerated data science or open USD development, okay? So, again, I don't really recommend those, but the top track I do. Just want to remind folks that certifications do not validate your programming, technical, diagramming, code management, and many other skills that are required to obtain technical roles. I do try to pack stuff into the course that are practical. So in this course, I have an NVIDIA RTX graphics card, and so I do utilize that a bit because we're never going to have access to that hardware unless you are really lucky and you have a DGX Spark, which is a very small form factor desktop version of the DGX system. You're really never going to be touching this hardware unless you work for a large organization. So, we'll do the best that we can here. How long to study for the certification? Well, if you're a beginner, maybe 12 hours. So if you have no knowledge of NVIDIA, or hardware or AI in general. If you are experienced, then, I think that you will be able to do this within 4 hours. Okay, so probably 6 hours study time, 50% lecture labs, 50% practice exams, 1 to 2 hours a day for 7 days. What I've noticed as a trend is that when there are new concepts coming out, like AI infrastructure, these courses tend to be really, really short because we're all learning the domain knowledge together. And so normally I'll make a course and it'll be like 20 hours, 30 hours, but there just isn't a whole lot to say in this because there just isn't. Okay, so all I could really produce was this 3.5 hour course. It's enough to pass it, and it's very, very laser focused to help you pass. But as I make iterations of a course, they get longer and longer and longer. But this is just where we are. Okay, so that's a great advantage to you because it shows you that it's very easy entry into this knowledge base right now. Okay, so I think it's worth your time to spend 3-4 hours or even 12 hours in a week and grab this knowledge, okay? So what does it take to pass the exam? Well, watch the video lectures and memorize key information. And specifically for this exam, there is key information, okay? The key information here is the data sheets, right? So the H100 data sheets, if you can get that data down, then it'll really score you a ton of points. But yeah, this is a very much key information kind of exam. We do have hands-on labs and follow-alongs, but they're very limited, and they're more for your benefit in this case than it is for working with the data center. So, I mean, we do get some hands-on with CUDA programming and using NVIDIA SMI to look at the graphics card and things like that. And if you don't have an NVIDIA graphics card, then this isn't going to be very useful. We could have spun up something in the cloud, but it's kind of a pain to get access to H100s or V100s. But we really need H100s to be able to do anything. So, we're just going to do our best to conceptually learn stuff. And again, it's a fundamental cert, so that's totally fine. Do the paid practice exams. This is something you absolutely want to do because the questions here are tricky. I would say that it's not a hard exam, but it really does hinge on knowing the data sheets, and they'll throw in words like technical words to try to confuse you. And then you realize that if you just stayed on focus of what the question was asking and not get thrown off by words you might not know, you would just pass, right? And so getting practice with practice exams are going to help a lot. And there is a lot of right sizing per se. So you do absolutely need to do practice exams, okay? Their provider is Certiverse, and there is no in-center, like in-person test centers. It's just online, it's fine. I like Pearson VUE or PSI online because they have in-person data centers, and I find those way less stressful. But here, your only option is the Certiverse. These are proctored exams, so you know the routine. If you've taken other exams, it's just a different provider, okay? The outline's really, really thin, or the domains are. There's only 3. It's essential knowledge, AI infrastructure, and AI operations. Each domain has its own weighting. When I designed this course, I was trying to chunk things into these 3 categories. It just didn't work, okay? So I don't know why, but it seems like the category topics are completely PR marketing, and there's just basically a bunch of stuff that you need to know. And so that's why in this course, there's literally a single chapter, and it's just a bunch of stuff, okay? And I've really condensed it down to just exactly what you need, and then we polyfill anything in, or fill in those gaps with the practice exams. But yeah, this structure totally doesn't matter. I think NVIDIA is less mature in terms of their certification development, but again, the knowledge is still pretty good. To pass it, you need 70%. Okay, they might use scaled scoring. We don't know, but they probably do. There's 50 questions. You can get about 15 wrong. There's no penalties. The format is multiple choice. The exam is 1 hour, 1.2 minutes per question. Your sit time or your exam time is 60 minutes. Sit time is 90 minutes. So seat time is the time you need to actually allocate for the exam. So that talks about time to review the instructions, show the online proctor your workspace, read and accept the NDA, complete the exam, provide feedback at the end. It wasn't very clear how long this lasts for, but I'm going to assume 2 years. NVIDIA, again, kind of hides these details, and I'm not going to trust AI's opinion on this stuff. I need to go to the source and tell you, but I think it's 2 years. I just want to remind folks always, and I always say this at the end of my certifications now is that cloud certifications expect you to have foundational skills in a bunch of stuff. And if you don't have that stuff, you need to go fill it. And so go get that free code camp, go get Exam Pro supporter subscription where we're filling in that knowledge. Certifications serve a structured way of learning with the goalposts. They don't necessarily always get you the job. But I would say that these NVIDIA certs, if you go for the pros, that will make you very attractive to organizations that are trying to do this, because again, there's few people doing it. But again, I just want to temper your expectations and make sure that you are focusing on rounding your knowledge and things like that, as opposed to relying on these certifications to getting you the job. But this knowledge is still really, really good. But anyway, there we go. So we'll jump into it, okay? Hey, this is Andrew Brown, and we are on the NVIDIA certifications page. I want to show you where the study exam guide is and give you my thoughts on how looking at it might help you understand, or might not help at all, understand how we're going to map that to the exam. You'll notice that NVIDIA breaks their certifications between the infrastructure professionals and the developers. We can say infrastructure professionals is like DevOps, but I guess it's more focused on people setting up infrastructure, as this is going to be for those that are setting up data centers or understanding the hardware behind it. The developer side obviously is a lot of the software. And for certifications, I decided to do the NCA AIIO course first out of all of them, because I thought that if you're going to learn about NVIDIA, it really should be about the hardware or the capabilities of what it takes to run these AI models in a data center. And that makes you appreciate the cloud offerings, but also if you need to consult on this for your organization, you'll have some sense of the scale and cost and the effort and the options and things like that. So we're going to go click into this one here, and we're going to scroll on down and make our way over to the study guide, which is here. They do have it broken down here as well, but it doesn't really provide the information we need to know. And so if we look at this, we have 3 domains at the top here that it's structured. This is very unusual for an exam. We usually see 4, 5, 6 domains, not 3. And the first one's kind of a bit of a gaffe because it's just generic information. But I would say that these aren't very well written exam guides or exam study guide breakdowns. And the only information we can really extract that helps us know what it is we need to study is the reference materials. So here they just have a bunch of generic, you got to know what NVIDIA is, but then down below here, it's like NVIDIA TensorRT. That is definitely something we need to know. But like the rest here, like you'd have to dig through like NVIDIA GPU operators. So stuff like that. Then going over to the AI infrastructure, again, they're not really telling us a whole lot here. But what's going to, again, tell us is this suggested readings like the H100 systems. It's interesting because there's H200, H300 already, but the exam, at least what I'm experiencing as of when I sat it, is still H100 systems, which is a great benchmark. I think there's a lot of H100s out there right now, as if you want something newer, it's not available, or it's really expensive and it's out of reach. NVIDIA Switch, definitely stuff like that. We'll scroll on down over to our AI operations. And here we have baseboard management controller, base commander, DCGM, working with Kubernetes with it. So MIG. And so I would say that this is not a terribly difficult exam, but it does require you to learn very specific information about NVIDIA. I think that if you learn the spec sheet or the data sheet of like H100s and the GGX system, that's going to get you very, very far in terms of this exam. And so you'll just see me try and like highlight very specific information points to just kind of help you out. On the exam itself, I noticed that they would throw in a lot of verbiage that had nothing to do with helping you determine what the answer is. It was just kind of throw you off. And so basically, if you get a question and you generally know something like, InfoBand allows you to, connect from GPU to GPU extremely quickly, they might throw in some other jargon in there that might throw you off. But if you just generally think, okay, well, what's this purpose of InfoBand and why do we want to use it? Then you can basically ignore all those words and basically deduce the answer. And that's what I was able to do, and I was able to do pretty well on the exam. So, I know this isn't very helpful, but it's okay because we're going to walk through the content, and by the end of it, you'll be okay. do the practice exams, as I would say my course here is a little bit light. It's not my most thorough job, but the thing is there's no certifications out here in the space for NVIDIA. So I'm really breaking ground here, and I just don't know how interested people are learning NVIDIA. And so this is just more fun for me to do. But I know a lot of people for the large cloud service providers or vendors were learning this, and so they'll probably be watching this. And hey, folks, hope you're enjoying this. But we'll see you soon, okay? Ciao, ciao. Hey, folks, this is Andrew, and we are going to talk about what is NVIDIA. I'm pretty certain you already know what it is, but in case you don't, it doesn't hurt to do a quick refresher, right? So NVIDIA is an American technology company founded in 1993 by Jensen Huang. I do not know how to pronounce his last name. He had two other co-founders, but he's the CEO, the front man. Everybody knows who this fella is, especially for him wearing these expensive leather jackets, which is interesting because before NVIDIA blew up in stocks, I don't think anyone was ever talking about his fashion, but you know, if you want to get a lot of attention on the stage, you have to create this public persona and have this kind of fashion statement. And so that is the approach that he took. NVIDIA was primarily known for their graphics cards, also known as GPUs, graphics processing units for video games. And so the first thing they produced is that NV1 graphics accelerator in 1995. Then they started the GeForce series with the GeForce 256 in 1999. And then their most famous graphics card of all time is that GeForce GTX 1080 Ti from 2017. I know this because I wanted one. I think I had like the GTX 900 or whatever, and this thing had come out, but I didn't have the money for it. But this thing was so popular, like all the way up to 2023, people were still buying it. And it was very capable for a good stretch of time. They have a lot of product lines, and they do things other than just GPUs, but this is generally what they're known for. And in the last 5 years, their stocks have just blown up. So you can see there how much they've gone up. And if you look down below, it says the market cap at $4.6 trillion. Okay, and the reason they exploded was because of the AI boom. Because to run LLMs, the best thing to utilize was NVIDIA graphics cards, and we'll explain why in just a moment. But anyway, NVIDIA has made a lot of acquisitions, and so you can see they've been very, very busy adding a lot of different types of technology across the board to their organization. But why is NVIDIA the leader in AI? So there's a very good reason, and most of it comes down to CUDA. So NVIDIA developed CUDA early, like in 2007, and allowed you to directly interface with your GPU via the API with lots of convenient libraries. And so they had laid the foundation to make their GPUs useful for general computing, not just for video games. And so data scientists and other folks could utilize them for other things. And so when the AI frameworks wanted to leverage GPUs, the CUDA framework became the default for when PyTorch was created, when TensorFlow was created, these big machine learning frameworks that everything was built on top of. And so that just kind of cemented NVIDIA graphics cards as the de facto, or CUDA as the de facto for developing this stuff. And so the other thing is that NVIDIA just heavily leaned into AI quickly. They had custom tensor cores, they supported early FP16, BF16, so lots of things like that. And so that's kind of the reason why NVIDIA has held the top place there, because it just works out of the box. And it's not that there aren't competitors that are better, it's just that that ecosystem is so strong that it's hard for anyone like Intel or any of the other chip manufacturers to get close to this space, okay? But there you go. All right, let's make sure that we understand what is a GPU. So a GPU stands for Graphics Processing Unit and is a processor that is specialized to quickly render high-resolution images and videos concurrently. That makes it great for video games. GPUs can perform parallel operations on multiple sets of data, and so they are commonly used for non-graphical tasks such as machine learning and scientific computing. So there on the right-hand side, we have an example of a CPU versus GPU, and I think it's worth comparing the two. So CPUs can have on average 4 to 16 processor cores, but GPUs can have thousands of processor cores. Okay, so when you see something like 4 to 8 GPUs, this can provide as many as 40,000 cores. So GPUs are best suited for repetitive and highly parallel computing tasks like rendering graphics, cryptocurrency mining, deep learning, and machine learning. So you can see why GPUs play a large role outside of video games in the AI space. There are other things that are specialized for stuff in the AI area, but the GPU has been a very useful thing overall, okay? Okay, so this course is focused on data center grade NVIDIA hardware, but I think that it's very useful to start with what you have because then you can kind of map that knowledge over. And so I'm going to be talking about NVIDIA RTX, which is the type of card that I have in my workstation. And so, if you have a different one, you might want to try to map it to yours and just have an idea of the capabilities of your card. And again, there's newer cards than what I have out here, but it's just going to be something to help us map our information so we best understand it. So let's talk about NVIDIA RTX, also known as NVIDIA GeForce RTX. It's a professional visual computing platform created by NVIDIA. So NVIDIA, they've had the GeForce series, maybe like GTX and things like that. So this RTX one is focused for professionals, not just gamers. And these cards are intended for professional use, like video production, product design, I don't know, something some math folks would do. You can still play video games on them, but they're really intended for professionals, okay? And when you have a brand like NVIDIA RTX, you're going to have a series of cards. And you can kind of see that they're releasing almost a series every other year. And then within it, there's a couple down there that's like workstation cards, server cards, obviously for smaller data centers. But since I'm just a professional consumer, I have that RTX 40 series. And though despite, me getting my new workstation in 2025, I have a card that is from 2022, and I'll explain why in a moment that I might have a card that's 3 years or 4 years older. But anyway, so within that series, there is a bunch of cards. And the card that I have is the NVIDIA GeForce RTX 4060. And then from that, when you have a graphics card, you have a specific board partner. So that could be MSI, Asus, Gigabyte, or in my case, it's an OEM system integrator, specifically Dell. Okay? And so the thing that you have to understand when you look at graphics cards coming from NVIDIA is that they design the chip. They don't generally design the cards, okay? So they're going to partner with another manufacturer who's going to take the chip, put it on a board, add fans, design a board in a very specific way. And so you'll end up with these, if you try to buy like a RTX graphics card, like RTX 4060, you'll be like MSI's 4060, Asus 4060, Gigabit's 4060, and that can be confusing because you're like, isn't there a definitive one? And technically there is. NVIDIA releases these things called Founder Edition cards, and so that's where NVIDIA specifically makes the entire graphics card. But they're produced in limited batches and availability because they really want you to go with the other consumers, but to get the ball rolling, they will release these. So I'm not sure how much more they are, but the point is that they do exist. But generally, NVIDIA, wants you to work with their board partners who are going to buy the chips and package them in different ways. And obviously, there are different capabilities between them, which make it really confusing to what to buy. So when I buy one, I just buy something and I shove it in my machine, and I hope for the best. But anyway, for me, I don't even have a board partner. I have this this one that is part of my Dell machine. So Dell is like a system builder, so they have like complete machines that you can buy. And the reason you might want to buy a complete machine where you don't have any control of the system, but it's fully integrated, is that you get really predictable support and reliable builds. So like Baco really likes Dell, my co-founder, and when I needed a new computer, he said, go get a machine from Dell. I think mine's an Optiplex, but Dell Precision is another one. But they said, go get this machine, and then when it breaks, they will send in 24 hours a a person to my house, and I live in a remote town, so that's crazy support. But they'll drive 2 hours, and whatever needs to be replaced, they'll just replace it on site, and I'll be up and running the next day. And so the thing is that when you work with a system builder, they're going to have their build around something very specific. And so you'll notice that this RTX there, the 4080, only has a single fan. So like they've clearly built it specifically for their machine to be very compact and fit in there. And so you might get older cards, but they're optimized for these things to be quickly replaced. So you're getting a trade-off of reliable build, something they know what works reliably, than having the newest thing. So even though like it's 2026, I got a card from 2022, but it still has ML capabilities, okay? Because when I got the station, I said I need to do some level of ML, and so, that's that. But let's talk about, my card, what's in it. So it is utilizing the Lovelace architecture, or Ada Lovelace architecture. That is basically the design of the card. Or the chip. We'll talk about that in a moment. And it features RTX 3rd generation RT cores, which is for ray tracing. Okay, that's great for video games, obviously. And then it has this 4th generation deep learning tensor cores. And tensor cores is what you need when you are working with ML. And just here's a photo of the RTX 4090 Founders Edition. I couldn't find a Founders Edition for 4080. I don't know if they make one for every single card, but I remember this one, and I thought when I would get my graphics card, it would look like that. It doesn't, but that's okay, because the ones made by NVIDIA look really, really cool. Let's talk about Lovelace architecture. So here on the right-hand side, whenever NVIDIA releases a new chip, they're going to make this cool graphic, and if you look in the middle of it, you can see the chips die. So that is a thin slice of silicon etched with billions of transistors cut from a larger silicon wafer. So just imagine them etching billions of transistors, okay, into a piece of metal, is the way I like to describe it. But anyway, let's talk about the capabilities here. So this is all the functionality of the Lovelace architecture. We don't need to know everything that it does here, but I've highlighted the stuff that is going to matter to us. So the version of CUDA is going to matter because it's going to determine what functions are available to us, and a lot of machine learning stuff is built around specific versions of CUDA capabilities. So you might be limited on what you can run based on your card because of what CUDA capabilities it has access to. Notice the tensor core, it's talking about the precision. So the precision is going to matter if you are trying to run specific models that have been built for specific precisions, okay? I highlighted NVLink because we learn about NVLink in this course, and it's saying there is no support for it. I don't know much about NVLink outside of the data center use in this course, but maybe NVLink is a consumer product as well for professionals. But we will learn about in this course about how it is much faster than PCIe, and that it's great, okay? So hopefully that gives you a frame of reference, and again, look up your card, look up its architecture, try to see if you can highlight the same things. But I think it's worth for us to go to the internet and take a look at maybe some leaked dies, because when you have these dies here, we don't get to see the full picture and all the capabilities of it, but it's fun to show you that people will go in and take up a close-up look and show you exactly what's being etched in here so you understand how these things work, okay? But there you go. All right, so I just want to show you some additional information about the RTX 40 series. Again, it's not about the fact that this is the latest thing. It's just more about show you how you can explore information. So we were talking about that Ada Lovelace architecture. And so if you type in die architecture, what will happen is that at some point, some company is going to try to figure out exactly how these things work. And so in this case, it's semi-analysis. And what you can do is you can kind of read through the whole thing and exactly understand what is going on here. And you'll notice that you'll see things like NVIDIA AD102, NVIDIA AD103, AD104. And if you go over to the GeForce RTX page here, you'll notice that we have variants where it says AD107, 106, 104, 103. It's telling you how many transistors are in that die, right? And so we're talking about transistors. It's when you look at that, and we're talking about those etchings, it's the stuff that is being etched into there. And so I mean, it can be a really interesting read going through here and just understanding, the capabilities of of it. So we're looking at the 8106. On the top, we see 16 times lane PCIe host interface. So PCIe is how it plugs into the board, right? If you've never seen PCIe on a board, it's these things. And over time, they have a lot of different versions and sizes of these. But the point is it's going to plug into your board, into your PCIe. So it's saying that's the host interface. We have the gigathread engine, which I don't know what it is, but I guess it manages the threads. On the left-hand side, we have 32-bit controller on both sides of it. In the interior, we have our cluster. You can see it has the raster engine. And so there's a bunch of stuff that's going on here. And then down below, you can see the L2 memory cache. So you can read in full detail if you want to kind of get a better sense of how this stuff works. And then this is more looking like the actual die itself. I'm going to see if I can, see, this actually really looks like a die. You know what I'm saying? So we'll just say like GPU die over here. And so normally what I like looking at is they'll have like the die up close, and they might even section it off in some videos to show you what sections they are. So you might see a die like this, and then there might be a representation of it, of the sections of what they do. Because it's literally how these dies work, right? So we might just click through this and take a look. I know this is not the RTX 4080, but sometimes they have an overlay. So, and I'm not sure if we can just type the word overlay. And yeah, so here's an example. This is the GeForce GTX 2060. Okay, and so we'll go here, and it can show you like this is what these parts are for. And so I think that's just kind of interesting, the fact that you can map that over and see it like that. And I just wanted to make sure that if you have never seen that before, you can read more about it, okay? All right, let's take a look here at the NVIDIA control panel. It is a pre-installed software app on Windows that allows users to manage and configure NVIDIA graphics driver settings and other GPU-related utilities. It provides essential tools for customizing display, 3D settings, video's performance, acting as a main hub to optimizing games and application performance. I just want to show it to you really quickly, just so that you can, if you ever forget like what type of graphics card you have, like maybe you bought a workstation like mine and you're not exactly sure, it will tell you what it is, and we'll peek around. Is it very useful for AI stuff and data center stuff? No, but we should know what it is, and it only takes 2 seconds to learn. So let's take a look at it, okay? All right, so here is the NVIDIA control panel. It came installed with my machine. I'm trying to think like when you install a graphics card, would you have to install it separately? I cannot remember, but I'm sure if you bought a graphics card, it'll have the instructions to tell you. But anyway, so I just opened up NVIDIA control panel, and right off the bat, it's telling me what version I have, and it's clearly indicating that I have the RTX 4060. Down below the left-hand corner, we have system information. So I'm clicking that, and it should open up some additional information. So we can see what DirectX version I'm currently running, the driver version, the driver type, the CUDA cores that are available with this graphics card, memory-related information. Okay, so all a little bit of information that we're going to want to know. So that is really nice. If we go over to components, we can see here a bunch of our settings and things like that. Okay, so lots of fun little things in here. On the left-hand side, we have options, but I believe we go up here and turn on developer settings, we'll even get a few more options. If we go into settings, we'll take a look. So here we have the spinning NVIDIA logo. We can adjust our 3D settings here. That's the preview, right? But here's a bunch of options. So like, see where it says CUDA GPUs all? So allows you to specify which GPUs can be used by CUDA applications. So you might want to limit what apps are using CUDAs, especially if you are sharing resources between them. So that might be something we might care about. That's not specific to graphics, but actually running our AI workloads. I'm just going through and seeing if there's anything else that might really matter for AI. No, not really. Okay, so I think here's a bunch of options we can turn on and off. Again, this is more for graphics, 3D graphics, right? Okay. We have powerful physics engine. Okay, so we have a physics engine here. That's fine. Let's go to developer. So restrict access to the GPU performance counters to admin user onlys or that. So not a whole lot of controls there. And we have some video settings. So nothing super exciting, but again, I just wanted to show you this because you can get your system information here and it helps you understand the capabilities of your graphics card really quickly, and it comes pre-installed on most machines that already have the NVIDIA graphics card, or you might have to get this yourself, okay? All right, so another thing that you should know about is NVIDIA app. So NVIDIA app is something that you install additionally that basically makes it really easy to manage driver updates. And in fact, when you first launch this thing, it'll actually ask you if you want to optimize for drivers that are either for creators or for video games. So that's really, really good. The thing is that it includes GPU control center and also recording tools. This is not going to be very useful for our use case for this learning, but if you have an NVIDIA graphics card, you really should install this thing. And that's why I'm showing it to you, not because it's super useful for passing this exam, but useful if you have an NVIDIA graphics card. That's just something that you should have, okay? All right, so if you want to install the NVIDIA app, you can go search for it, install it. And so I already have it installed. When it started up, it gave me an option between focused on video games or creators. I chose creators. And right away, you can see that it's detecting what's in my library of programs. So what it detects and decides to detect, I don't know. But like here, you can see, I've actually never played this game yet, but let's say we go to Cyberpunk. And we have all the in-game settings that we can see from here. And if we hit play, we'll run it from here with these optimized settings, right? And so we can go over to OBS and notice that it is uplifting those settings. And again, we can launch it through here to get the best value or settings for our graphics card. And so this is a really, really great thing. If we go over to our drivers tab, we should be able to see our driver version and whether we need updates. So here, I'm just seeing if I can make sense of this. There's a newer version, right? So there's a newer version. And notice here it says game ready driver or studio driver. So that was the two options I'm talking about that it will set up. And down below, you can read about those options. I obviously don't have the latest stuff set up, but if you notice here, NVIDIA studio driver support. So it says, well, broadcast. Broadcast is a program that is for capturing your camera into the NVIDIA card to add like AI backgrounds and stuff like that. But here we have Comfy UI. So Comfy UI is something that is used for graphics pipelines for generating out images on your thing. So that is definitely AI related. LTX2, not so much related, but you can see there are some relevance to what driver support and stuff that you bring into here. If we go to system settings here, I rarely ever click this, but I guess it's giving us information about power and temperature and other stuff. There's another way that we can get information about our graphics card that I normally utilize, which is via the CLI using the SMI tool. And we will look at that in later in here. And we go to the rig and we're getting similar information that we were seeing earlier. So you can see I have 64 gigabytes of RAM, i9. Oh, this is the game ready driver. So I guess whenever I install this first time, or maybe this is installed, so I don't even have the optimal one for what I want to do on here. So I got Windows 11 Pro. I'm working with 3 screens. Okay. I'm not sure if there'd be anything else over here. Manage GPU counter performance. I don't think we'd ever want to fiddle with that. Yeah, there you go. Nothing too confusing here, but again, something that you should install as it is very useful. And you can even see there's apps that we can install right away, but nothing specific to what we're doing, okay? But anyway, ciao, ciao. Let's take a look here at NVIDIA SMI, which stands for System Management Interface. It's a command line utility bundled with NVIDIA GPU drivers used to monitor and manage GPU devices. So this is something that, if you have an NVIDIA graphics card, even on your own machine, and you are running ML models or things that are intensive, this is a great way to get real-time information about how your graphics card is performing, or just getting information about your graphics card in general, though I did show you via the control panel in the NVIDIA app how to do that if you're in a data center with no user interface, graphical interface, then you'd be using SMI here. So it provides real-time data on GPU utilization, memory usage, temperature, power consumption, essential for tracking performance. It supports Linux and Windows 64-bit. So these commands I'm going to show you, you should know what they do and remember them, because there's a high chance they might show up on your exam. Okay, and so I'm being very deliberate here to show you very specific ones, not all the commands, but the ones that you absolutely should know. The first is dynamic monitoring. So you type in DMON, dynamic monitoring. Notice you get the GPU, the power, the temp, the memory, additional information there. We have process monitoring. So this is showing what processes are running. So maybe you have Python 3 running something, and notice there's a PID number so that you could, kill the PID or whatever. Then we have query-specific details. So if you need to get very specific information, memory usage, memory total, or temperature, or very specific things, you can do that. Notice that you can format things as CSV, so you can export it out into CSV format. This thing, and we'll learn about MIG later, but MIG is the capability of taking a GPU and isolating it into segments for different uses. Again, we'll cover MIG later on, and that will definitely be covered. In this command, you're going to want to know. So when you cover the MIG section, come back and look at this command. But the idea here is that with MIG, we're going to create GPU instances of a specific size and profile for MIG-capable GPUs. So things like the A100, the H100, those ones, they are MIG-capable, not my RTX. That can't do it. But really expensive graphics cards where you can logically isolate them into separate things, we can do that. And when you utilize it, you're going to be utilizing a very specific profile. Okay, and so see how it says 0, 1, 9, 14. So that's the number that you're putting in here, and that's going to determine different parameters for that segmentation. So CGI creates a compute instance with a GPU instance, right? And the C flag specifies the compute instance profile ID. Okay, but anyway, when we cover MIG later on, just remember this and come back and learn these flags, okay? There's another thing in NVIDIA SMI. When we first use it, it'll give us a bunch of information. I don't have a screenshot for that right now, but I'm gonna go over and show you NVIDIA SMI with my RTX, okay? All right, folks, we're going to take a look at NVIDIA SMI. When we installed the drivers with NVIDIA, it should have installed NVIDIA SMI. So if we need to get it to work on Linux, we can absolutely do that through WSL, like Windows Subsystem Linux, or if you're on a Linux machine, obviously that's a different story. I would say that most people that are working with NVIDIA graphics cards as a consumer are going to be more familiar with it on the Windows side of it. Because when you're dealing with containers or containerized environment like Windows Subsystem Linux, there's some extra things you got to do to access it, and it's kind of a bit of a headache. I do believe we cover some Docker stuff in this course, specifically for getting access to the graphics card through a container. So I'll try to include that here, but not in this video, but we'll try to do that because that was a big pain point for me when working with making sure I'm utilizing my GPUs in a containerized environment. Let's go ahead and type in NVIDIA SMI. I believe that's all it is. So we type in NVIDIA SMI, and right off the bat, we're getting some basic information. So we have the version, the driver version, the CUDA version. So notice that earlier when we were looking at Wikipedia, it said it was 8.9 compatibility. And so I'm guessing that was the lower threshold, right? So it wasn't that I couldn't use newer versions, that I just can't use anything older than 8.9. I believe that was the version. But here you can see I'm running CUDA version 13. What other information here? So here you can see if anything is in use currently. So these are our processes, and we clearly have 4 right here. Some additional information would be, I guess this is its use over here. Let's see here. We got GPU fan, name, temperature, preference. Well, anyway, we got usage. It'll make more sense once we start working with it, but let's go ahead and try some of those other commands, okay? So I think we had NVIDIA SMI daemon. Okay. And so that's reporting that information there. And we can see its temperature right here, 28. I'm going to assume that's Celsius. I don't know. Memory percentage being utilized only at 12%, so nice and low. I'm assuming that's for encoding, decoding, JPEG. I'm not sure what the other ones are for. But what we normally care about is temperature and memory usage. Okay, so we'll stop that. And we'll type in clear. Let's go ahead and try NVIDIA SMI PMON. NVIDIA SMI PMON. It's not supported in this configuration. Interesting. Okay, so I guess maybe I can't utilize it on my NVIDIA graphics card. That's kind of interesting that there are ones that you're not allowed to use it, but we do have a screenshot of it, right? And you also notice over here, when we went up to here, we have it right here. So the only thing is that it's not actively monitoring in real time. Let's take a look at the queries works. We'll say NVIDIA SMI -- query GPU equals memory used, and then memory total. Okay, and see, we go ahead and hit enter. And so we're able to get that exact information. We can try a few other things here. I'm just going from the PowerPoint slides that I was able to grab. These are the default examples in a cheat sheet that I found. Temperature GPU. I don't want to pretend that I have these memorized, okay? Power draw. We'll go ahead and do that. So you can see that information there. Say NVIDIA SMI -- query GPU equals name. Okay, we can get the exact graphics card. I think I said 4080. I guess I have the 4060. I'm not paying attention, am I? I'm going to open up the control panel. I thought I had 4080. Oh, I have a 4060. And in the slides, what did I say that I had? Did I say I was richer than I am? Let me go take a look. I mean, that is a 4080 here, but I guess I thought I had a 4080. I said 4060, then I said 4080. I guess I'm getting mixed up. They sound really similar, so I guess I have a 4060. But anyway, that's SMI, and you should know those commands. Even though we can't do the PMON here, we should know it. We could technically try to spin up a GPU in something in the cloud. That might be a little bit hard to do. But the point is that, if we're in the cloud, we should be able to utilize the same interface in Linux, and get different kind of information. We could also try to start running something to get a sense of usage here, but I think you understand that these numbers will go up when we are utilizing some kind of GPU stuff. But I think that was kind of a hard thing, is that when I was utilizing stuff here, I wanted to make sure that I was using the GPU versus the CPU. And I'm not sure if I exactly remember how to do that. Show them side by side. There's probably some kind of user interface thing that we can utilize, but obviously we can access through SMI, or we have the NVIDIA app as well that gives us some stats. But there you go, okay? All right, let's talk about CPU cache levels, because it's probably a good idea that we understand how caching works at the CPU level and also the GPU level. We'll cover GPUs later. But most CPUs have a hierarchy of multiple cache levels, and they'll name them as L1, L2, L3, L4, and there's other types here, but generally those are our levels. And so on the right-hand side is a representation of a CPU, and you can see it has 4 cores, and each core has its own L1 cache, and then underneath that we have L2 cache, L3 cache, DRAM, which is a type of cache, and so that's the CPU. So let's address these L1 to L4 levels. These are actually static random access memory, or SRAM. This holds its data permanently until the power is turned off. So if something's written, it'll hold it until you turn that computer off. It's used for the cache and internal registers of a CPU, and it's going to be faster than DRAM. So let's talk about at least the first 3 levels of cache. I'm not sure what level 4 cache would be, but generally this is what the 3 levels are. So for level 1 cache, this is located as close to the CPU core as possible, and has the high speed due to a short signal path. For L2 cache, this is physically separate from the CPU. It operates slower, but it can place fewer demands on the chip. It can be made much larger without impacting the CPU design. For L3 cache, this is generally shared among multiple CPU cores. We have DRAM, so dynamic random access memory. This decays in seconds and must be periodically refreshed. Used for computers' main memory. So when you're working with lower level programming languages, you have control to write to exactly what cache that you want to. When we start working with CUDA, generally knowing what's getting written to where is important, but it's going to be more focused on the GPU side. But there is interactions between the CPU and the GPU, so we should generally know what these things are, because you'll constantly see like L1, L2, and DRAM, and so it just helps to just kind of spell this stuff out, okay? All right, let's take a look here at CUDA. So CUDA stands for Compute Unified Device Architecture and is a parallel computing platform and API by NVIDIA that allows developers to use CUDA-enabled GPUs for general purpose computing on GPUs, also known as GPU, okay? And you saw earlier with my RTX graphics card that it is CUDA-enabled. So I mean, I don't know of any NVIDIA graphics cards that aren't CUDA enabled, but if there are ones that aren't, I'd be surprised. Here's some examples. If you know AWS, here's some examples of NVIDIA graphics cards that you could access in the cloud, like Tesla V100, M60, T4, A100, things like that. All major deep learning frameworks are integrated with NVIDIA Deep Learning SDK. And so the NVIDIA Deep Learning SDK is a collection of NVIDIA libraries for deep learning. And one of those libraries is the CUDA Deep Neural Network Library, so CUDNN. And so CUDNN provides highly tuned implementations for standard routines such as forward and backward convolution, pooling, normalization, activation layers. So what I'm trying to say with that end part is that, and I said this earlier in the course, was that, the reason why NVIDIA is doing so well in the AI space is that, they made CUDA, and CUDA has this library within it that just made it really easy to start working with their hardware, with parallel computing, especially on general compute. So, hopefully that is clear. If you want to know a little bit more about the vision behind CUDA, there is a white paper from 2008 by Lindholm, and it is very interesting and has some nice graphics in there. So I just wanted to point you to it, and it goes a little bit deeper, more about graphics, but it still is very relevant to AI portions of it. So it's up to you if you want to read it. I just want you to be aware that it does exist. The way we're going to install CUDA is via the CUDA toolkit. So you just go ahead and you download it, and it's going to give you, make sure you have the drivers or whatever the compiler you need for it. I think it's called NCCL or something, the compiler. But CUDA is typically coded in C++, but there are wrappers for higher level languages like Python. It doesn't show there on the right-hand side, but I know there's a .NET wrapper as well. But we will look at some comparisons in this video of what it looks like to kind of use Python as a wrapper and make it a lot easier to work with. There's a library called QPy, and this is a Python library that basically gives you the functionality of NumPy, SciPy, but it leverages CUDA underneath. And so we'll definitely look at that in just a moment. I want to talk about like the architecture behind CUDA, and I found it very hard to make sense or understand it, so I had to break it down a little bit differently as I was really blanking out there on the internet trying to make sense of it. So hopefully you like my explanation a bit better. But on the right-hand side, you have a CUDA program. I'm just going to get my pen tool out here. Okay, so here at the top is your CUDA program, and then down below you see GPU. So these are your GPUs, and each GPU, they are distributing the workload into their compute, okay? So the idea is that the compiled CUDA program has 8 blocks up here, okay? And the CUDA runtime can choose how to allocate these blocks to multiprocessors, as shown with the streaming multiprocessors. Notice based on how many SMs there are in the GPU that the blocks are being eventually, but I mean evenly. I spelled that wrong. It's supposed to be evenly distributed. And some other terms that kind of confused me, but I figured it out eventually, was when they're talking about host, specifically when they're talking about CUDA, they're talking about the CPU on the system. And host memory is the CPU's memory. If they say device, they're talking about the GPU. And they're talking about device memory, they're talking about the GPU's memory. Okay, so those are some broad terms we should know. But what I want to do is I want to break down exactly what is a CUDA block. So let's take a look at that. And so the idea is that you have first a CUDA thread. So this is your lowest level unit of parallel execution for a kernel function. And generally, you're going to have things organized as a block. And so that's a collection of threads. Okay, so they might call it CUDA block or CUDA thread block. And they come in numbers. Well, before we get into that, we'll say the idea is that when you have all these threads, you want to execute it against some piece of code, and that's your CUDA kernel. So I spelled kernel wrong here. It should have an E on this. But your CUDA kernel, it basically is just a function, usually written in C++. It's a function that performs some kind of mathematical operation, and it's going to run it across all these threads within your block, okay? And generally, you have these blocks made up of 32 threads, a block made of 32 threads, and we call that a warps. I didn't look up what warps stand for, but it's called a warps for whatever reason. And a warps will run within a streaming multiprocessor, which we'll see in just a moment. Then we have CUDA core. So the idea behind a CUDA core is that it's a simple arithmetic execution unit inside the streaming multiprocessor that performs integer and floating math for CUDA threads. So CUDA core is not like a CPU core. It's much smaller and simpler, and it's operating on things like floating points, integer math, basic arithmetic stuff, okay? So hopefully that is clear. If we go up a bit, we were talking about these streaming multiprocessors. So the idea here is that you have these SMs, which are the core execution unit inside the NVIDIA GPU that runs warps of CUDA threads. And so an SM contains the CUDA cores, tensor cores, load, store units, registers. We're just focused on this one right here, okay, CUDA cores. And so for this SM, it has a couple CUDA cores, and this one has a couple CUDA cores. But when you think about all of the CUDA cores across the entire SMs, that's what we call a CUDA grid. So a CUDA grid runs across multiple SMs, and a CUDA grid maps to a single GPU, okay? Individual thread blocks are scheduled onto individual SMs, as you can see here in the vertical lines here. So hopefully that is clear when you look at those diagrams. If it doesn't make sense when you see those architectural diagrams, just come back to this explanation, and this will break it down a lot faster. There are some debugging tools that are worth knowing when you're working with CUDA, like NSIGHT, GBD, and memcheck. They're not going to show up on your exam, but I just wanted to point out those three so that we can add those to our toolkit if we need to figure some stuff out. I wanted to show you some comparisons of code. So here's an implementation of a CUDA program, and it's written in C++. And generally, these things are written in C++. C++ isn't that hard to write, but if you want to use Python or .NET, you absolutely can. And so we need to define our kernel function. So that is the function that's going to run across threads. As you can see, it's not complicated. It's just this one's adding two arrays together, right? So whatever small repeatable thing you want to do across a bunch of stuff. Notice that in CUDA that we're managing the memory ourselves. So see the CUDA malloc, and then we have CUDA malloc device to host and things like that. So that's why I said, why did we want to learn the word host? That way we know that we're talking about the CPU, right? So we're learning those little terms. But let's take a look if we were to use Python instead. So this is the PyCUDA as up here. But notice that we're still using C code here. So even if we were using PyCUDA, we still have to define our function that runs on our threads in C++, but at the very least now we are using Python to manage it. And so the syntax is a little bit nicer, but again, you can tell it's not that hard to do C. And we're still manually running our memory. Now, if we were to do something like Numba will greatly reduce the amount of code. And so now our function, our kernel function is written in Python. We have this CUDA.jit, just-in-time compilation, which will turn it into basically, not C++, but whatever the machine end code is. And so you can see this is a lot shorter, right? Also, we're not really managing the memory. It's kind of doing that indirectly for us. So we get some automatic memory. And then we have QPy, right? And notice that we don't even have to define a kernel here because the kernel is going to get outputted somehow based on the operations that you're doing. We're doing no memory management, and so all these pieces of code are the same. But I just wanted to make clear that CubePy makes it like dead simple. So if you're in the data science space and you're going, I don't want to write C++, that's too much for me, and I know Pandas, this is how easy it will make it for you. Okay, but yeah, we should understand the interactions of memory for CUDA. So we saw earlier the CPU memory. Let's take a look at the GPU side of memory. So you have registers. These are private to each thread compiler, and they're not visible across threads. You have your L1 shared memory. This is a fast on chip memory, just like the CPU memory, shared with CUDA blocks. Physical resources shared across blocks on the same SM. We have read-only memory. So this is per SM instruction cache, constant memory, texture memory, and RO cache, read-only in kernels. We have our L2. This is shared across multiple SMs. Okay, and we have a global memory. And so this is the largest but slowest memory tier. And so, I'm saying that you basically are always working with these memory caches. And if you are working C++, you generally want to know how you're interacting with them. So this is what it's going to look like when you're interacting with the global memory. So we're doing CUDA malloc. So global memory is really, really slow, but it has the largest capacity. You have your shared memory, and that's how we're accessing there with the shared keyword, if you'll notice here. Yep. And, shared memory is very fast, but it has a small capacity. You have your constant memory. Basically, it's read-only, but it's super, super fast, but it's also super, super small. You have your register memory. Notice as soon as we do int, that's putting it into the register. So that's how you're utilizing the register. It's super fast per thread. And then you have local memory. This is where it looks like you're using the register, but you use a very large value. And so it ends up placing it into that instead. Okay. For a CUDA processing flow, that's generally good to know. You copy data from the main memory to the GPU. Okay. So I'm trying to find my pen. There it is. So here, main memory to the GPU. CPU initiates the GPU compute kernel. The GPU's CUDA cores execute the kernels in parallel, okay, copying the results of the data from the GPU memory to main memory. So there's things you got to know about memory. But again, for this course, this isn't this certification is not about knowing how to write CUDA in great detail, but you come across it so much, you really should know it when you're in this NVIDIA ecosystem, and that's how we're covering it. The challenge here with CUDA is that there's many versions, and CUDA has different features per version, okay? So it's not uncommon to having to work with multiple CUDA versions, but managing multiple CUDA versions is a little bit tricky, and we'll talk about that in a moment. But you can see over here, I'm trying to find my pen tool, that we have the CUDA versions going all the way down, and you can see the coverage. So we have Tesla, Fernie, etc. So mine, I have an Ada Lovelace, right? And we know its capabilities starts from 8 all the way to the latest, okay? So remember when we looked at the data sheet for, or the feature set for Ada Lovelace, it said it was 8.8 compatible. And so here it's indicating that at the 8 or 8.5, which is unusual because over here it's the 8, down below here it's the 11. So I'm not really sure why it does it that way, as we know that it can go a little bit farther back. But generally this is the supported range that we have for that thing. So yeah, you can definitely get locked out of features. And sometimes there can be features that only exist in a very specific one. So you can run into that kind of issue. The CUDA SDK provides a low-level API, the CUDA driver API, and a high-level API, the CUDA runtime. And here you can see in CUDA 8, these are all the packages that are part of it. We said earlier there was CUDNN. I don't see in this one, but we'll continue on here. Maybe it'll show up in this one here. This is number 9, number 10, 11. Okay, so maybe it's not directly in there. I thought it was in there. But the point is you can read each of these and see, okay, this is CUDA fast Fourier transform library. So a bunch of data science math stuff that's very useful, right? That's kind of built in and works right away. Notice that sometimes there are things that are deprecated and then they're renamed in a later version. So you can run into issues where there's things that only work with very specific versions. So how are we going to be able to change our CUDA versions? Being able to upgrade, downgrade when we have different programs that were designed for very specific versions. Well, CUDA doesn't have a version manager, but it relies on environment isolation. using Conda Mamba, which is a smaller version of Conda, and Docker. And so basically, here we're using Conda and we're creating environments and we're saying, I'm using this version of Python, but I want CUDA 118. Or here, we're specifying the toolkit as the general way that you, this is just the name of the environment. This is just the name of the environment. This is actually the way you install it, because the way you install CUDA is through the toolkit. And here we're saying, I want version 11.8. And so you basically make a bunch of environments and switch between them. And that's how you would do that. And at some point in this course, I think we'll show you Docker, because there's more to it than just saying install it. But if you are using Docker, this is just a Python isolated environment, but Docker, there's more work to map it over. But anyway, hopefully that gives you an idea of CUDA. Again, it's not something we need to 100% know, at least not for the time I'm making this course, but we should know what it is. Okay. Hey folks, this is Andrew Brown. This video, we're going to take a look and try to build ourselves our own little CUDA program. I figured it's a good exercise to make sure that we are familiar with what we got here. So I'm going to go over to the CUDA toolkit. We'll go ahead and download the latest version. So here it says CUDA 13, et cetera, et cetera. I mean, technically we should be creating environments to manage this. So I'm just trying to decide what I want to do here. One thing I can do before I start doing anything is I can just go check command prompt. As I might just do this on the Windows side to make it super easy. But we can say NVCC. And so it says it doesn't recognize the program. And so what I'm going to do is I'm going to go ahead and go to Windows. I'm going to go download it for x86. And I'm on Windows 11. And I'm going to download it for local. And we have our toolkit at 2.3 gigabytes. And then it's talking about the driver if you've yet to install the driver. But I guess while we're doing that, we should go over to our... there's a few ways we can do this. But I'm going to go over to our control panel for... NVIDIA, because I have to remember what version of CUDA I have here, or CUDA capabilities. And so if I go into here, one second, you'll notice here we have driver type DHC, driver version, And so what I'm hoping to look for here is like CUDA information. We said CUDA cores, sure. Another thing that we can do is just do NVIDIA SMI, CUDA version 13. Okay, so what's up here? 13.1, so we are in good shape. We'll go ahead and use the CUDA installer. And so we'll wait for that to download, okay? All right, so that's download. We're gonna go ahead and give that an install if I can make my way over to wherever it is. Just a moment. And it's, come on. I don't know why it's giving me a hard time here today. But we'll go over to my downloads. I'm doing this off screen, obviously. And so I'm just double clicking and launching CUDA toolkit. And I'm waiting for it to open up. Oh yeah, I definitely clicked it. It's going. There we go. And so we'll go ahead and hit yes. You can see that it is now extracting it out. And so we're doing everything on the Windows side. I personally prefer working in WSL Linux, but I don't want to overcomplicate things just yet. And so until I need to do that, I'm going to just do it on the Windows side. If you're on a Linux machine, like without Windows, it'll be a lot easier for you. But if you're trying to do Windows subsystem Linux through Windows, you might have some trouble here. So we have Express or Custom. Ooh, we can do Custom. What are our options? And so here we can choose our runtime, our libraries, development, compiler. Okay. There's the NVCC compiler that I was talking about earlier that I didn't know the name of. What other tools do we have? Okay. NSite, which is for debugging. So we're already going to get that. And so we'll go here, look at the runtime, and these are all the things we want to install. So go ahead and hit next. And it's going to place it into NVIDIA GPU computing. Okay, that's fine by me. We'll hit next. And I'll say I understand. That's fine. I don't care about Visual Studio, but I just left it checked no matter what. I guess that makes sense because like Visual Studio is a program for writing C++. So I was just going to try to use Visual Studio Code, but we'll give that a moment here to install. All right, so to install Visual Studio, that's fine. Yep, that's fine. We're fine with that. I think this should be a non-issue, as I believe that we can use MVCC from the terminal. So what I'm going to do now is I'm going to go back over to command prompt, and I'm going to assume that we can access it from here, NVCC. Let's type in hyphen version. And so I'm just going to close it out. I'm going to reopen up command prompt. You can't see this, but I'm opening it up in administrator mode, just in case. And we'll go ahead and type NVCC hyphen version. Okay, so now it's showing up and we see CUDA. Okay, so that is good. And I guess the next thing is we need to write a CUDA program. So CUDA programs, I believe, have the extension .cu. And so I'm just going to go quickly use something like ChatGPT and ask it to generate me out some code. So just give me a moment. Okay, and so now I have a little bit of code that I will bring onto screen right here. So we definitely have one. I'm just going to first go open up Visual Studio Code so that we can start working with this somehow. So I just need to make a new file here. And I'm going to grab this code here. And we have hello from kernel 1 block threads, wait GPU to finish. That's not very exciting. I would have thought that like we would have done something that actually looked like something. Okay, can we actually perform a kernel function? Okay, because that's what we should be doing, right? I'm not sure why it's doing that, but we'll give it a moment here. All right, so here it's doing add vector. We're just trying to find anything. As long as you have some kind of function and we're going to run it, and it's doing the malloc and etc., then you know you're on the right path. So this looks to me, this looks like CUDA code. So we'll go ahead and grab this. And I'm going to bring this over here and paste it in. Oops. And I'm going to just save this, save as. I'm going to save this to a new folder. We'll call this CUDA examples. And I'm going to save it here. And I also just going to CD back out here for a second. CD CUDA examples. Oh, it's actually literally saved as CUDA examples. So I'm going to make a new directory called CUDA. Well, sorry, we'll move CUDA examples to test.cu. We'll make a new directory called CUDA examples. And then I'm going to move the test CUDA into the CUDA examples. I'm going to CD into our CUDA examples, and we're going to do code period, just so that we can focus on this code. There it is, good. Don't save for now. Okay, and so we have our code here. Just bump this up a bit. And we'll open up terminal. Well, that's the only challenge here is that this terminal here is not going to have MVCC, is it? Well, let's just take a look. Does it? Oh, it does. Okay. I'm in WSL right now, I believe. So for whatever reason, it seems to be detecting it from the host system. So if it works, that is fine. But I was assuming that we'd run into some issues. Okay, so here it's suggesting to compile it. I'm going to make a new file here called readme.md. By the way, folks, if you're watching this, do your best to try to follow along. You know, sometimes I can provide code, but this is so small, and you should try to do this on your own. That I don't necessarily think that is important. So MVCC should compile that code. So we'll go ahead and we will, we'll grab this. We could make this a CMake file or whatever, but we'll just go ahead and see if this actually works. Oh, it's not called add vector. So I'm going to rename this to add vector. Okay, and so now we actually have our program. Vector add, and we'll run it. And so we get some output. And so it's adding up vectors. So we look here. Here it's printing the results. So yeah, the program works. Could we observe this? I don't know. We'd have to do something a lot larger, computational, and run it against it. But for the purpose of what we're doing here, I think that this is probably, you know, a good hello world, so to speak. If there's a reason for us to do more CUDA, we can. But I just want to show you, like, it's not hard to get running with it, you know, and, you know, we didn't really talk about memory management or all that other stuff, but that's your hello world for CUDA, okay? Ciao, ciao. All right, let's take a look here at ResNet 50. So ResNet 50 is a basic backbone vision model that can be used for various purposes. And the reason we're covering this specific model is that I saw it a ton on the exam. And also, it's just such a generic or all-purpose model that you see a lot in a lot of examples. You should know what it is. So on the right-hand side, you can see the visualization. I can't remember the name of the visualization tool, but there's tools to visualize out models. And so you can see it's really, really long. And you can see a close-up view of how that works. I'm not going to explain how the model works in this video. I'm going to tell you what it does, but I'm not going to explain the math behind it and stuff like that. But anyway, so ResNet 50 is a convolutional neural network that's great at image classification. The ResNet 50 belongs in the ResNet or residual network model family. So there are other variants like ResNet 18, 32, et cetera, et cetera. So ResNet 50 was released in 2015. The model size is around 100 megabytes. ResNet is small and can run on hardware from 2016. So if you have a 4th generation Intel Haswell CPU, you could run on that. If you have a 2017 iPhone, so an iPhone 8, if you have a GTX 700 for a Series 2013, it'd be slow, but it would work pretty well. And so you can run this thing, and that's why it's so popular, because it does a really good job for that task. It doesn't matter that it's an old model, because old models doesn't necessarily mean bad models, but it just hit a certain point where it was very, very useful. So ResNet 50 could be trained to run on your phone and detect a dog in a photo. For some reason, with ResNet 50, they love in every example to talk about a photo dog, but there's a website here, TensorSpace, which gives you a visual way to explore that model. And so they give that example there. ResNet 50 Onyx model included with the Onyx Model Zoo. So what I'm trying to say there is that Onyx has a bunch of models, and they have an Onyx model specifically for ResNet 50. So that is what we're visualizing there on the right-hand side. So I ended up downloading that model and utilizing it. But Onyx is like this standardized format for representing models. And we are going to learn about Onyx in this course, but that's ResNet 50, okay? Hey, this is Andrew Brown. I just wanted to quickly show you TensorSpace, because you can go and see the visualization of how ResNet 50 works. And here you can see that it's predicting that this is a dog. And if you go over here to this, you can see it's predicting ice cream sandwich. And so you can see all the 50 weighted layers. And if you click into any of them, you can kind of see like how it's starting to try and detect it, in different ways, okay, as it narrows it down to the final conclusion of what it is. So, yeah, I mean, I'm not the best at explaining it, but I can just show you that there is a visualization and there's something happening here, and it's cool. Would it be useful for us to learn ResNet 50 on our NVIDIA graphics card? Sure. I'll have to make a decision if I want to include that. Right now, I'm not sure, but if you do see a video that follows this, then you know that I've decided that I thought it was useful to get some NVIDIA practice. But for now, I just want you to know what ResNet 50 is, because you're going to see it again and again and again and again. And notice that the model, like, it's only 100 megabytes, right? So think about that a model has to live in memory, right? And so if you have 100 megabytes of memory, then this thing can live in memory, no problem. It will have no issues with inference. But there you go. All right, let's take a look here at the NVIDIA Container Toolkit. So this is a collection of libraries and utilities enabling users to build and run GPU-accelerated containers. And this toolkit contains the container runtime, the toolkit CLI, the CDI hooks, the container runtime hook, the container CLI, and the container library. So a bunch of things collected in there. You don't need to remember them all, but just know that there are multiple things in there when you are using it practically. And so when you have this toolkit installed, it's going to make it really, really easy for you to leverage the GPUs on your host system. I wish I understood this a lot sooner, as I used to see these flags quite a bit when I was working with containers and models, but I never really connected that it was with the NVIDIA Container Toolkit. So very useful that we can see that there. But up there, we're seeing sudo docker run, and we are setting the runtime as NVIDIA, and we're specifying to use all the GPUs. And all this Docker is doing is it's through Ubuntu, it's running the NVIDIA SMI command, which we already learned about. And so it's just showing through the container that we're able to access the information about the GPUs. And again, I really wish I knew this a lot sooner. But there are some options that you would want to know from a practical standpoint, but also you might get these questions on your exam. So it might distinguish between these parameters. So it's very important that you know them. And so I've specifically handpicked these ones to help you on your exam, okay? So one thing you can do is you can select your GPUs for use with the GPU flags. That is the old-fashioned way to do it. That's the way that I always knew how to do. Or you hyphen GPUs, say, I want to access all of them, okay? Another way that you can do it is you can specify the exact device. So numbers are going to be assigned to your device. A device, as we said earlier, is another term to say the GPU, right? And so we're saying device 0 and 1. So we're selecting two devices, two GPUs in this case here. And then another way that you can do this is you can enable the container device interface, CDI, and then you can specify your device using device flag. And this is the recommended way of doing it. So just getting my pen tool out here for just a moment. You can see here we're saying device, and we're saying nvidia.com/GPU, and then we're saying equals all. So a different syntax, but for whatever reason, it's recommended. The container device interface is a specification designed to standardize how devices like GPUs, FPGAs, and other hardware accelerators are exposed to and used by containers. And so I believe that this is specific to Docker. And so here, NVIDIA Container Toolkit is utilizing that Docker feature. That's how I understand it. But the thing that I want you to remember is this GPU's device and specifying it this way, and the fact that you can do device and then just say what you want to specify, right? It probably would have been better if I used an example of using a very specific GPU here, but that's what I got, so that's all right. But anyway, we should do this in practice. Of course, if you don't have an NVIDIA graphics card, this might be hard. You could probably go to the cloud and try to have something that has a GPU attached and try to run it. But I'm just going to run this on my local computer. If anyone wants to try in the cloud, please tell me if you're able to do it in the comments or wherever on this video. I'd love to know. But anyway, let's go see if we can access our GPUs through a container. Okay, ciao, ciao. All right, so this is a retroactive video. So the next video after this is a lab. And so this stuff was so painful for me to figure out that I'm front loading this lecture information because you don't want to watch the whole lab, but how to get this thing working. This is something I've been trying to get to work for like over a year. And I had one environment that works on my other computer. I've never been able to figure it out till just now how to do it. But let's take a look at exactly what it's going to take to get this thing working. The first thing you have to consider is that when we're talking about the NVIDIA Container Toolkit, I'm specifically saying using it within WSL2 within a Docker container, because that is how you're going to want to use it, right? And if you have to use it other ways, that's fine, but you're not going to be able to know for certain if everything's working as expected. So what I would recommend is I would suggest to install or create a new WSL2 environment. So here I'm doing Ubuntu 22.04, okay? And then we export it, unregister it, make a new directory, and re-import it. And the reason we have to do all of this is just so I can rename it so it has NVIDIA. Because I want to know that once this is working, I have an environment that I absolutely know works, and I can rely on it, okay? And then this last line just runs the environment. You also have to install Docker. I showed that in the video, but I'm not showing it here in the steps. The next part is that NVIDIA SMI should already work. Okay, so we didn't install the NVIDIA driver into this environment. It automatically should pass through from the host. And so when you run NVIDIA SMI, this should work. Okay, that might make you think that this is ready to go, but that's not necessarily true. One thing that I found in the instructions was really confusing is that the CUDA toolkit and the NVIDIA Container Toolkit, they look very similar names. And I think the reason I was spinning my wheels is that I thought I was installing the NVIDIA Container Toolkit, but I actually was installing the CUDA toolkit. I do believe that I ended up installing the CUDA toolkit, but says you don't need it, and I don't think you need it. And it's not hard to install. It's just like writing this command here, just like NVIDIA or like CUDA toolkit. But anyway, we install the NVIDIA Container Toolkit, and then we want this line. This line's super important. It's going to set the runtime, because the line I kept getting was like, oh, there's no NVIDIA runtime. We don't know what you're talking about. And so I was endlessly getting that issue. Then we need to restart the container, and then we can do this. Now, I just remembered that I actually didn't test the other ones with the device, and the CDI mode. And the CDI mode is obviously more preferred, but I was just so excited getting this one to work. I didn't think about it. So I don't think I'm gonna go shoot the additional one there. I don't think it's necessary. But anyway, I wanted to put this forward because this was such a pain for me. And at the end, it was ChatGPT that picked up the right information. I did go through the docs initially. That's how I like to do stuff. But it just had some of the commands. I can't exactly explain why we can't find that online easily. But the point is that we solved it. And so I hope it solves it for you. And that is going to be a large enablement for you, okay? Hey folks, this is Andrew Brown. In this video, I want to see if we can utilize the NVIDIA Container Toolkit. And so there's a few things we have to consider, and it's like, where are we installing it, right? So there might be a way to install on the Windows side. Primarily, the way I would want to work on my local machine with this would be through the Linux experience, which is, you know, the WSL, Windows Subsystem Linux, or WSL2 in particular. And so we have that additional layer that we need to figure out. And so supposedly there is this guide here which will help us through this. If you don't have this, then this is going to be a little bit difficult for you. The other solution you could do is try to get access to an NVIDIA graphics card on the cloud. I find that kind of a pain because anytime I want a graphics card, I need to increase my service limits, and then I'm always waiting for 1,000 years. So I think just to make it really easy, I'll show here on this one. And we just want to prove that it works. So if you have a NVIDIA RTX graphics card or something that is able to do it, that'd be great for you to test out here. If not, just watch along and we'll see what we need to do. And so here in the guide, it is going to say that we need to have WSL install, which we do. Here's saying install the NVIDIA driver GPU support. It's specifically talking about GeForce Game Ready or the RTX Quadra Windows 11. Now earlier, I think we were looking at the NVIDIA app, right? And I think I was saying like, oh, I think I might have the one I didn't want installed, which was the game one. So if we go over to, where is it, settings here? I'm trying to remember where it was. Graphics. No, not here, system. We're looking for that driver information. We saw it earlier. Oh, drivers maybe. And so there's the studio driver, right up here. It says it wants the game ready driver. Can I just switch between them? Oh, I don't know now. Okay. But anyway, here it says GeForce Game Ready driver. And so that's what it's asking for. So this is the one I'm supposed to have. And so what I think I'm going to do is I'm going to update my driver. Last time I updated was April 16th, 2025. So just give me a second, I'll be back. I'm going to do a really risky thing and update my driver, okay? And it's still updating here. It's not taking very long, but we're going to see what happens. I would think it needs a restart. Now it says install. So we download it. Let's go ahead and install it. We say yes here. You can't see it off screen, but it says yes. Upgrades current drivers and retains existing ones. That sounds good to me. I like that. And normally when you update drivers, you're supposed to have a backup recovery point in Windows or whatever. Probably supposed to do that. I never do that. I've never had any problems. Maybe this will be the first time I have a problem and I'll regret not doing that because I'm jinxing it. But we'll see what happens here once it updates, okay? All right, so it's done. I did have to restart my system. What's really interesting, though, is that OBS, my recording software, crashed. I still have the original first part of it. And so we've updated that driver, that game ready driver. I don't know why the other one might not work, but you can't always trust NVIDIA's documentation as, I mean, they have good documentation for a hardware provider, but it's, you know, not the best. So we have that all the way up to date. And so that is now, that requirement's now out of the way. I already have WSL2 installed. I already know that I'm running it. I already know how I can get into my WSL environment. The question is, how do we get CUDA support for it? And so this will be the next section. Let me just give it a read. Okay, and so I know this text is really small, but let's just bump it up here. And the key thing that it's saying here is that if we're using WSL2, and I am using WSL2, that it's already supported. And so it's saying here, I think it's saying that if you're using a prior version of WSL or a preview, you have to do a build specifically with the CUDA toolkit. but I'm pretty certain I have it. So once NVIDIA GPU drivers install the system, CUDA becomes available within WSL2. So apparently, instantly it just happens. CUDA driver installed on Windows host will be subbed inside the WSL2. So as of here, therefore, users must not install any GPU driver within WSL. So we're not putting anything on the inside. See, I would have thought that we would have had to, right? But if it just instantly works, that's great. One has to be very careful here as the default CUDA toolkit comes packaged with the driver, and it's easy to overwrite the WSL NVIDIA driver, so that's why we don't muck with it. We recommend developers use a separate CUDA toolkit for WSL available over here to avoid overwriting this. So I don't think I have to do anything. First, remove the old GPG key, so we don't have to do that. Installation of this, so that's whatever. So what are constraints? WSL2 GPU acceleration will be available, etc., etc. Ensure you're on the latest WSL kernel, or at least 4.19.121. I'm not sure how we would check that. If we open up command prompt on this Windows machine, and folks that are on Mac, well, I don't know, Mac, you wouldn't have an NVIDIA graphics card, would you? But anyway, so what we'll do here is we want to know about WSL. So if we type in WSL, we might get some information about it. No, it actually just put us into WSL. So say WSL, I'm not sure. So find out what kernel version WSL2. How do we find that out? Oh, it is hyphen version. Okay, that's what I was going to do. It's frustrating when you want to do that. Now, you can do that via PowerShell or here. It doesn't matter. And so here we have kernel 5.15. So what was it specifying for? It is specifying for what? Kernel version what? 4.19 or 5.10. So well above it. Windows 11. I'm on Windows 11. If you continue with Windows 10, etc., known limitations. So Maxwell GPUs are not supported. So I don't think I'm using Maxwell, but let's go take a look. Remember, there are different versions of it. If we go to CUDA Wikipedia, I think it kind of tells us the range of these things. Right? So we go here, we go, okay, Maxwell. So I go, I'm pretty sure that I'm using Ada Lovelace, which is all the way over here, and Maxwell's all the way down here. So this is like a 2014 graphics card. So if you're using something really old, like 2014, well over 10 years ago, you're going to not be able to use this. So that's fine. Unified memory, fully managed support is not available. I don't think that matters. Pin system memory, I don't think that matters. Root user on bare metal, not containers, doesn't matter. With the NVIDIA toolkit for Docker 1903, only GPUs all is supported. So it's going to matter what version of Docker we're on. So now what I'm going to do is go over to Visual Studio Code, usually often with WSL, when you have it installed, and you should have it installed. I'm not showing how to do that here. They have the instructions there. That we can take a look here. So if I drop down here, like I'm in Bash, so I know I'm using WSL2 right here. So I want to see what Docker version I have installed here. I'm not showing how to install Docker either. And we have version 27.51. So we're totally doing fine here. And I don't have to use this GPU's all mode. So that's really good. Features not supported yet. So the following table lists of the set of features that are currently not supported. So NVSMI does not support all queries yet. So it is supported, but just not all queries. OpenGL CUDA interlope is not supported yet. For our exam, this stuff doesn't matter. We are doing this for hands-on because I know this is super useful when you start trying to work with workloads locally. So that's why we're spending the time here. Okay, so we already have Docker working here. And in my instructions, in my PowerPoint presentation, we have a command, this one here, and we're going to run that and see if it works. So we'll type in. Now, normally if you install Docker, you might need sudo. I've changed my Docker, so I do not need sudo. I'm not going to show that, but that's fine. So go ahead and type in --rm, and I'm going to say runtime equals NVIDIA, and we're going to say --GPUs all, and I'm going to say Ubuntu, and we'll say NVIDIA SMI, and we'll hit enter. So here we have an issue. It says NVIDIA SMI, unknown or invalid runtime NVIDIA. Okay. I mean, that should work. So what we'll do is go up here and we'll take a look. And so they have a command here. So I guess we really need is the full path. I mean, that's an example of one. In some cases, running the container, you may encounter this. No. So I want to go NVIDIA SMI container. Because there should be a command here that's saying it's not found. There should be a command here to run it. NVIDIA SMI is now supported, but in order to use it, you have to copy it manually to the user bin directory. Really? That can't be right. Well, first of all, let's just see if we can do NVIDIA SMI in here. Okay, so we have NVIDIA SMI. I didn't install anything on this thing, and so we are able to access NVIDIA SMI in WSL, but I want to run it within a container in WSL. That is my end goal, okay? That's what I want to do. So we will go back over to here, and I'm trying to figure out how we can get that. So over here, we have the NVIDIA container runtime. That's the thing we're trying to run right now. And we scroll on down. So Docker is the most widely used one. So we have Docker, sudo, run, whatever. Let's go ahead and just try this. Okay. I feel like this should just work. What am I missing? Docker run requires at least one argument. Well, according to them, it doesn't. Run CUDA container from Docker Hub. Yeah, because it should pull the NVIDIA container from there. But over here, it's saying Docker run requires at least one argument. Let's go ahead, and we really shouldn't have this. We'll do sudo. But yeah, it looks like it's not even specifying an image, right? Normally, you'd have the image name in here, and it doesn't look like we have it there. That's why we had Ubuntu earlier. So I wish they would just give us an example. We'll follow through into the toolkit here, and maybe we'll find some information on it. User guide. Please don't bring me to this website. Yeah, it brought me to the, nope, different site. Okay. And so what we're looking for is literally the command to run it. That's all I want is the command to run it. It's got to be somewhere here. Running a sample workload. We'll go over to here. Okay, so this is the one. So this is exactly the same. It looks like it's exactly, that's probably where I got it from. Sudo, and you can see that I obviously got it working at one point. That's how I took that screenshot. So we have sudo docker run rm runtime NVIDIA GPUs all Ubuntu NVIDIA SMI. So I'm not crazy. We'll go ahead and we'll try this again. Unknown daemon or invalid runtime NVIDIA. I must be crazy. Okay, give me just a moment, okay? All right, so over on the Windows documentation, or Microsoft, they're saying, and look down here, it says, enable NVIDIA CUDA on WSL2. Remember that we read that it said we didn't need to install the GPU driver on the WSL2 side, so I'm hoping that it's going to tell us we don't have to do that. So Windows 11 and updates includes PyTorch, et cetera. This includes, as well as Docker and NVIDIA Container Toolkit support available in native Linux environments, right? And this computer is only a year old, and so it should have a version that is up to date to have this. But download and install the NVIDIA CUDA enabled driver for WSL. But we said we didn't need it, but now we do. So we'll go over to here, I guess. Conflicting information, right? We're back over here. Okay, so clearly we're missing something here. Install the driver. We did this. Right? This is the only driver you need to install. Do not install any Linux driver, display driver in WSL. As far as I'm aware of, I have not done so. Launch your preferred Windows terminal, command prompt. Ensure you have the latest WSL kernel. We could do that, but it says that we have a version that is the latest that we need. Set up a Linux developer environment. The latest NVIDIA Windows GPU driver will fully support WSL2. With CUDA support in the driver, existing apps can run unmodified in the WSL environment. To compile new CUDA applications, a CUDA toolkit for Linux 86 is needed. CUDA toolkit is support for WSL is still in preview stage as developer tools such as Profile is not available yet. However, CUDA application development is fully supported in WSL2 environments. So maybe it's saying it's supported, but you still have to do something. As a result, users should be able to compile new CUDA Linux applications with the latest CUDA toolkit. Okay, so maybe we do have to do it. So once NVIDIA GPU drivers is installed, we have done so, CUDA becomes available within WSL2. It makes it sound like it's already there. The CUDA driver installed on the Windows host will be stubbed into the WSL2. Therefore, users must not install NVIDIA GPU drivers with the WSL2. One has to be very careful here as the default CUDA toolkit comes prepackaged with drivers. And it's easy to overwrite the WSL2 NVIDIA drivers with the default installation. We recommend developers use a separate CUDA toolkit for WSL2 Ubuntu, available over here. Pages to avoid this overwriting. Okay, so let's go over to here. Wait a second. This is so confusing. We recommend developers to use a separate CUDA toolkit for WSL2. So that makes it sound like we do have to install it into WSL2. But then they say users must install the GPU drivers. Oh, so I think what it's saying here maybe is that don't install the drivers separately. Install the CUDA toolkit, which will install drivers on WSL2. But I was thinking that it just gets inferred through it. And so there's probably where the confusion is. Option 1, install the Linux x86 CUDA toolkit using WSL package. Okay, so the CUDA WSL local installer does not contain the GPU drivers. So by following the CUDA download page, you'll be able to get the CUDA toolkit installed in WSL. Okay, so let's do that. And so we're over here, and we have a bunch of links. And we have Linux x86 WSL Ubuntu 2.0. So it knows exactly what we want. And then we have our installer type. I don't care. Let's just get it working. Network, I suppose. I think we want just local, right? Because that will download and install. But this one's easier though. Yeah, we'll do it this way. So we'll go ahead. I'm just gonna grab all 3 of them. or all 4. I'm gonna be real dirty. I usually don't do that, but we're gonna go for it anyway. And we're going to paste that in and let it rip, okay? And we'll give it a second. All right, so we've gone ahead and the toolkit should be installed here. Let's go take a look and see what happens if we go back and run this command again with the sudo all. And so we're still getting this issue. Okay, so the toolkit is definitely installed. But the other thing is that we were able to do NVIDIA SMI before. Good question. Because if the toolkit was already installed and we were already able to do, if we just installed the NVIDIA toolkit and ran NVIDIA SMI, does that come with the driver? Just give me a second, okay? So what we're gonna do is, I'm just gonna see if we can just restart our WSL. So I'm stopping mine here, and then let's see if we can get this back up again, WSL. I think that if we go back to Visual Studio Code, it might just launch it for us. Okay, so I'm just hoping that it automatically triggers WSL. Go here, make a new one. Notice that it is hanging. Okay, we'll just write WSL. I never remember the WSL commands. Like this will get me into WSL. I mean, we could also just do it from here. We don't actually have to use. Visual Studio Code for that. But we can go ahead and I will try that command again. I promise you, getting this to work is worth it. It seems like a random video in this course, but it might be the most useful video in this entire course is getting this to work, seriously. So I'm going down here, I'm looking for that individual command. It is not that one. It is not that one. Where is it? This one here. Okay, so we'll grab this. I don't need sudo, but we'll go ahead and try it anyway. I'll just take that out. And it just will not, it will not let me do that. So the only thing I can think of is that, maybe I had the driver installed here prior, and that's where it's running the issue. The other thing is that maybe we could create a new WSL environment and then install it there and we'll have less of an issue, right? So that'll be something we need to figure out. So I'll just how to create a new WSL environment. Okay. And I'll just go over to here. And so we'll just try this really quickly. I wasn't going to do this, but obviously you can now see what we're doing. I want to leave my other one intact. And so maybe this will just be a CUDA one. So we'll do this. But can be installed with the sudo apt-get not found. Oh, no. Oh, it's because we're in WSL right now. Okay, so we'll reopen command prompt. I'm opening in administrator mode. It's like a button. I can't show you. It's on my other screen. And we'll go ahead and we'll try this again. And so I know it's already installed, but I want to install another variant of it. Okay, so what I'm going to do, we're going to go ask Claude or ChatGPT, I suppose. It doesn't really matter which one. We'll go here. So I need to a separate Ubuntu version to rule out NVIDIA drivers. What's the command to install Ubuntu as a separate environment and name it with NVIDIA? And let's see if we can get that command there. Yeah, and it depends on the version. To then rename it after the export import. Okay, well, that's what I want to know. I want to do the list. So we'll go over to here. We'll take a look. --list, --online. And I'm just type exit here. WSL --list --online. And it says Ubuntu. We have 24.04. Looks like the latest that I can install. If we go up to here, that's what I want. Then rename it after the import export. They're not explaining that part of it. How do we rename it? Let's install it normally. Export it. Well, that looks complicated. But this is the only thing I can think of because I've been having this problem for a long time. It works on my other computer, but not this one. I just want to rule it out. So now I'm literally installing another one here. And so we'll just give it a moment here. Hopefully it doesn't override my existing one. If it does, that's a bummer, but we'll see what happens, okay? And by the way, it's going really slow. So it is progressing. There we go. I think initially it was downloading, now it's installing. So I was just going to say it's going like it was going to take forever, but maybe not. Here it wants a name for the new Linux. We'll just say Andrew. And then we'll have a password. I want to have no password. Can I have no password? Oh, it wants me to have one here. So I'll put in a password here. Obviously, I'm being secretive about it. And so in theory, we should have one installed. So let's go ahead and we'll say WSL Ubuntu --list. Sorry, --list here. Oh, we're inside of it right now. I think. Let me go exit it. Okay, so we'll go ahead and we'll try this again. I think list here. And so this is the default one, WSL, and then there's the 22.04. So I believe that's the new one that we just installed. And so I'm going to go ahead here and we're going to go and say WSL export 2204 like this. Which is silly that we have to do it this complicated way. Okay, that's now exported. We're going to go ahead and unregister it. And before we do that, I'm just going to scroll up and see what we had before. I can't. Well, let's hope I don't blow anything away. And so we have here where it says unregistering, the operation is completed. And then we'll re-import it back into here. Assuming that these are the same paths, I believe that it is. And we'll go ahead and try that. Yeah, because it can't find it. And that's what I was wondering about. So yeah, like, where's the pathing? Like, it obviously isn't there. You didn't tell me to do that. You must create a destination folder before running the import command. What? What do you mean I have to unregister, export, WSL import from here, etc., Ubuntu. Well, hold on a second. What if I do ls or pwd? dir. Oh my goodness. Sure, why not? It's confusing that this says PowerShell because this one's clearly PowerShell. We'll go ahead and we'll do that, I guess. Make sure the tar file exists, dir. It does, I believe, based on what I'm reading here. I mean, I don't really want to put in system 32. I guess that's just where I was, right? And what we'll do is we'll go back to this other command here where we're importing it. Great, now we're importing it just so we have a rename. And it's now imported. We'll do WSL -list. And so now we have one that says NVIDIA 2204. So what I'm going to do is going to go back over, well, I guess we can just launch it now. Let's say we want to use that. So that's what I'm looking for now. It's to use it. So we'll go here and just say WSL help, because I don't know what the command is. Like, how do I specify which version I want to use? Okay, how do I launch it now? It's probably WSL followed by the name. That's what I'm thinking. Well, very close. So it looks like it has a -d. Unless -d means to run in the background. -d, set it as the default. No, I don't necessarily want it as the default, but it looks like maybe -d as set defaults this. I'm not sure if that's the same command. What's the -d command for? It's probably distribution. Distribution, that was my guess. We go down here. It could have been short for default. That's why I have to double check, right? So go ahead and we'll run this now. And so we're waiting for this to start up. Did I hit enter here? There we go. Oh, wait, hold on. We'll do clear. I don't know what's going on here, so I'm just going to close that out. We'll try that one more time. So say command prompt, run this as administrator. Yes. We'll go back over to here. Oh, it's not listening to me here. We'll -d Ubuntu 2204. Sorry for the small text. It's very hard for me to bump it up, unfortunately. And so we have that. We'll say NVIDIA and hit enter. And I think we're in there, clear. There we go. Definitely looks different, which is fine. Yeah, the default one has like nice coloring and stuff. So let's type in NVIDIA SMI. And so off the bat, we already have that information here. So it says CUDA version 13.1, driver version, NVIDIA SMI, NVIDIA GeForce RTX 4060. So it knows I have it. Do we have Docker? There's no Docker. Okay, good. So now I'm going to just type in exit. Because I'm just curious, did I blow away my old one? If I just go ahead and say WSL and hit enter, do I get nice colorings and all that kind of stuff? Yes, so my original one's still intact. But I'm going to go ahead and type exit again, and we're going to go back up to here. And so this one doesn't have Docker installed, so I guess I'm doing everything from scratch here. So we'll go ahead, Docker install Ubuntu. And we'll get this installed quickly. So I guess you folks are getting a little preview. I can't tell you how many times I've installed Docker. So many darn times. But we'll do it again. So install from the app repository. This is the official way to do it. And this is the way that I would normally do it. Add the GPG. So we'll go ahead and do that. Can I bump this font up? Nope. Nope. It will not cooperate with me. What I'll do is we'll go back to Visual Studio Code because we're now running that there. And so we should be able to access it here now. So that is starting that, which is fine. But I don't know which one it's running. This is probably the default one. This is the default one because we have our beautiful coloring. But if I go here and we say new terminal, I should be able to, if it stops closing out here, I should be able to choose that other one in here somehow. Well, it's not letting me switch it. Usually you would see the options here and then you could switch them. But it's not doing that here today. Bash, tmux, bash, origin, split terminal. So it's not being very clear. We also have this option here, WSL, connect to WSL. So this is like WSL remote, so we can switch to it. I'm gonna click on this. I mean, it's already connecting, but I want to connect to a very specific version, right? So I'm going to go back down to here and we'll say connect using distribution. So we'll click this one here. And so now I'm specifying the NVIDIA one. So now we can do that, and I can bump up that font and we'll have a much easier time. So that one's now running here. We'll go ahead, we'll go to terminal. Okay, I'll hit enter and let's go get Docker installed. Shouldn't take too long. Okay, so this one is going off the screen here. And then that's done. So we'll do the next section here. Add the repository to the app source. Okay, so just pasting that in. That's running. That's already done. We'll go down below and we'll grab the latest version. We're getting Docker Compose plugin, Docker Build X plugin, Containerd, so a bunch of stuff with it. That looks good to me. I'm happy with all that. It's a little bit hard to select, but we'll grab that. I feel like the last time I installed it, the instructions were a little bit different, but that's totally fine. Capital Y, so it just forces everything along the board to install. Okay, so that is going there. And so now that is installed. And so we'll do sudo docker hello, what was it, like hello world? Hello world. Is Docker installed? It is. Docker hello world. I thought I needed to make it sudoless. Yeah, sudo. I always forget to do like Docker hello world. Let's just type that in, hello world. And if we go here, oh, run. I forgot the keyword run. Yeah. You think like with all the courses I've made, I would already know how to do it, but no. I want to see if it's sudoless. I think it worked sudoless, didn't it? That's really nice. Normally, I have to run sudo in front of it. So I'm not sure how the instructions change that, but whatever this new instructions are for installing, that was really nice because I didn't have to specify sudo. So not sure why, but I'm not going to complain. So we don't have the NVIDIA toolkit installed. The NVIDIA SMI thing works in a new WSL environment, which is really interesting. So what we want to do is go back over to that command, which was not here, over here. Where is it? Here, this one, and then we'll give this one a try. So fingers crossed that it works. Unknown runtime. Unknown runtime. All right. Oh, well, hold on. We didn't install the NVIDIA toolkit, right? So it's a new fresh environment, and it's saying that we're supposed to install it, right? So we'll go ahead and we'll grab it. 13.1, I'm assuming, is the latest one. I can't imagine it would take us to the oldest one. So we'll go back over to here. We'll try this. Okay, so now this is installing. And we'll give it a moment to finish. All right, so we have the NVIDIA toolkit installed. And so in theory, this should work. And it just keeps telling us that there is no runtime environment. Like, this is driving me insane. Okay, so we've ruled it out that we have a fresh WSL environment in there, WSL2. We can see that it already is accessing the driver from the other side. The only thing I can think of is like restarting my computer. I'm not sure why I would have to do that, but we did install a new driver. But clearly we can see that is access to there. We installed the NVIDIA toolkit as per instructions, even though it's a bit conflicting. So there's something that's missing here, but give me a moment, okay? I'm gonna just go off screen and try to solve it. So everyone's talking about sudo as the issue, but this one's saying in particular that there is a configuration for rootless. And over here it says, I had the same issue, NVIDIA runtime not being recognized in rootless mode. Turns out there's a specific Docker configuration for rootless mode over here. I mean, technically, I believe we're setting up to rootless because I'm not having the sudo in there. But normally when I install Docker from scratch, I have to say I want to not use sudo, which I hadn't had to do this time. But here it says, to configure container runtime for Docker using rootless mode, follow these steps. Configure the container runtime for NVIDIA CTK. NVIDIA CTK runtime. I don't even know what that is. We haven't touched NVIDIA CTK, which is not even a command, apparently, even though I'm pretty sure we installed Let's go back to the top here. So I'll be back in just a moment. I'm going to, like, maybe the toolkit's not even installed. Well, hold on here. What happens if we did CDK, it says command not found. What if we put sudo in front of here? Because we definitely installed the toolkit, right? It installed, right? Updated, running. Did we not install it? I could have swore we installed it. Okay. How do we confirm NVIDIA toolkit is installed? Oh my goodness, we didn't need that photo there. MVCC could be it. I mean, that's the compiler though, isn't it? MVCC. Hyphen version. I don't think that's correct. Could not be found, but can be installed with the NVIDIA thing. So maybe we actually just never installed it. So here it says, yeah, we did this. If I go back to here and try this, the latest version is installed. Okay. We'll go over to here. Okay, so how do we do our sanity check? How do we know? Oh, hold on here. Run the installer. Running the installer sudo should, hold on here. So perform the installation, reboot the text mode. We concentrate number 3. Reboot the system. Sure. We're not rebooting our actual system. We're just rebooting this one here. So it's now going to reconnect. Maybe that was the way we could have restarted it earlier. I just didn't think of doing that. So maybe it'll reconnect here. I've never done a reboot on WSL, so I'm not sure if you can do that just like a regular machine. Seems upset that I did it. We'll just go ahead here and try this again. And so I believe it's been rebooted. We'll go here to terminal. Terminal. Oh no, I buggered it up. We'll go ahead and command prompt here. And we'll say WSL -list. We'll say WSL. I think we learned earlier that it was like shut down. And then we could specify the distribution this way. -D like this. And so now what we'll do is we'll go ahead and restart it. And so in theory, yeah, it should be running now. We'll go back over to here. Try this again. It should establish a connection here. Sometimes that messes things up, so we'll go back over to, I'm telling you, it's really worth it. You think I'm crazy, but if we get this working, it's a big deal. So we did that. We did the reboot here. What was the command? It was like this, that can't be found. Yeah, so, I mean, we could also just install it like DNF, like they had there. Or apt-get. I just don't understand because we already installed it. Let's go for it. Sudo apt install. We really shouldn't have to do that because we used the correct way of doing it, toolkit here. And it's installing it. It looks almost the same. It's like 13.11 NVCC version -v. So here, to avoid automatic upgrade and lock down the toolkit to the next version, that's probably why we're installing that specific version. Driver installation, basic instructions, installation, perform the pre-installation actions. This can be accomplished with number 3, consult your system, reboot. CUDA uninstaller, no. Oh my goodness, this is like very hard to get working. So what I'll do, say what can we do to check if NVIDIA toolkit is installed on Ubuntu WSL, e.g. NVCC. Yeah, but we know that NVIDIA SMI works, right? So we go here, right? We get that, no problem. Then we have NVCC version. I mean, we didn't do having version, but it says it's not found. Okay, we get this. You should expect this. This is an issue in your Windows driver, not your Ubuntu. You should see the GPU. If this fails, it doesn't fail. Check if CUDA toolkit is installed. I guess the tool, oh, that's the CUDA toolkit. That's separate, right? If installed, you'll see something like this. If you get that, command not found. CUDA toolkit is not installed in the distribute. Check if CUDA libraries exist. Okay, but do we need CUDA toolkit for the CUDA container toolkit? So there's 3 layers of the WSL GPU system. We have Windows, WSL GPU support. We already have that. CUDA toolkit, optional. You're compiling CUDA code. We're not. You need the MVCC command. We don't. What about the toolkit for Docker GPU at WSL? We need it. The container runs its own thing. We can try this command, which is giving a very specific version. I don't think that's going to work. This one's not saying runtime at all in here, though. Still pulling the image, though. Could not select drivers. Yeah, and so that still doesn't work. Are you running Docker inside of WSL? Yeah, yes. Right? Installed into Ubuntu, which is confusing because it says you're supposed to. You only need the Windows driver plus the NVIDIA tool. Oh, yeah, well, we know that. We know this, right? So we go down here, confirm WSL sees the GPU. We know that it does. Confirm the Docker version is installed in WSL. We know that it's installed. It's right there. Install the WS toolkit. We've already installed it like 3 different ways. Let me go hit up and just see what command we ran. No, that's the tool. That's the CUDA toolkit. And then we go back over to here. Have I just been installing the wrong one this entire time? Oh my goodness, have I been installing the the CUDA toolkit? Please tell me that's not what it is, that I'm just like super, super dumb. Okay, so what I'm just gonna do, because maybe that's our problem, maybe we just haven't installed this entire time. Please tell me I'm just dumb. Okay, and then we'll go back over to here. So here we have, I'm not sure why we'd have to run this. What's this for? Tells Docker to use the NVIDIA GPUs by registering the runtime. Okay, well that sounds good to me. Nowhere did I see that other places. Config file does not exist. Wrote it is recommended to restart the Docker daemon. And so that was the second instructions we had. We'll go ahead and try this. There we go. And so now what we'll do is we'll go ahead and I'm looking for, not that one, the real nice one we got. This one. Oh, is it working? Is it working? Yes! Okay, so there you go. I'm going to go make a slide. You're going to already have watched this video, but I'm going to go make a slide of that video and just get this stuff up front because that was such a headache and I cannot tell you how much I've been struggling with that. But anyway, the reason why this is really useful is that, you know, if you are trying to work with NVIDIA and WSL and containers, and a lot of times you'll find containers online that just you have workloads, this is the stuff we run into, okay? But anyway, that's all I wanted to accomplish here. So technically we're able to run this. Maybe I will go and now make the Resonant 50 video, as I really wanted to make that, but I did not want to run it the other way. I wanted to run it, through a container like this. And so I might come back and try that in a separate video. But yeah, we finally accomplished what I wanted there. So there you go. All right, we're taking a look at Triton Inference Server, and this is an open source inference server. I don't know why I don't have the R on the end there, but it serves the model so you can make inference. And I know it sounds like I just said what I mean, but the easiest way to think about it is like, think of a web server. A web server serves up web pages. So an inference server will serve up a access to a model to go make a prediction or inference and come back with something. And I believe that they market this probably as like an enterprise solution, that it's open source. It's good for any cloud provider, et cetera, et cetera. So we have that nice big diagram on the right-hand side where it says NVIDIA Triton Inference Server, and it has parts in it, but let's go take a look here. So Triton supports inference across cloud data center, edge, and embedded devices that are running NVIDIA GPUs. It works for x86 and ARM CPU, so technically, my computer should be able to do it. AWS Inferentia, which I believe is AWS's own silicon for AI acceleration. You can deploy the model using TensorRT, PyTorch, Onyx, OpenVINO, Python, RapidsFill, and more. And the Triton, I know it's hard to say, inference server is part of the NVIDIA AI enterprise. So there's that AI thing. But yeah, these things are not normally that complicated to use. A lot of times you'll download a repo, or you'll just run it through a Docker container. And there's a lot of inference servers out there, but you should know that the only thing you have to really remember is that Triton is an inference server, and it's for calling your LLMs, okay? And it serves up your LLMs, okay? All right, let's see if we can use this Triton inference servers. I've used inference servers before. I haven't used this one, and so it's saying here that it should be able to do it, but I'm not using enterprise-grade equipment here. I mean, I could spin up some compute here, but let's just see if I can actually utilize it locally, because they do have a simple example here, and it looks like it's using DenseNet Onyx as the model. So my question would be like, what requires DenseNet? So let's go ahead here and just look up DenseNet, because I just don't know what that model is. And what might help here, I'm just going to do this off screen for 2 seconds. We'll go to ChatGPT, and I'll just ask like, what model is this? Is this something I could run on my RTX 4060? Because I imagine this is a very small sample, but I'm not sure. I don't remember all the name of the models. It's almost certainly a DenseNet, yeah, image classification exported to Onyx format, and yes, you can run on 4060 easily. Good, so that's all I want to know. So what we'll do is go over to here. I assumed it was something we could run, because they want you to be able to run this on some kind of consumer hardware so you know that it's easy. So here's create the example model repo, launch it here, and see we're running it through Docker. And the good thing is that because I solved the thing with WSL earlier, if you didn't watch that lab and get that set up, you might want to do that. I should be able to run this containerized within WSL2. Okay, sending a request, and we should be able to do that. So let's see if we can get this working. So go over to Visual Studio Code, just because it's a bit easier to work with. It's connecting to my NVIDIA one, which has the NVIDIA Container Toolkit installed onto it, so that should make my life easy. And I'm just going to look where we are right now, PWD. Do I got like a home directory or something? We'll go to Andrew here. This is a fresh machine, so make directory, I'll just say sites, and we'll go here, and I'm just going to clone that, assuming I have Git in here. Git, is it there? Yes, it is. Can I clone it? Let me clone it. If it's public, should be no issue here. There we go, we're cloning it. Hopefully it's not too big. We'll CD into the server. There we go. We will fetch models. Not exactly sure what that's doing, but I'm assuming it's downloading the actual model. Inception v3, yeah, I'm not exactly sure. Once that's done, I can just do code.period, and then we can see the structure of what it's downloading. So we'll just give that a moment to download. Okay. It actually looks like it's doing more than downloading the model. It looks like it's getting all the dependencies and everything that we need. I'm not sure if it's creating that virtual environment. I don't see that here, but it could be doing that as well. All right, that only took, I don't know, a few minutes, so it wasn't that bad. And so we have the model, clearly download the model. The model's small, it's only 44 megabytes. You got to consider the size of the model is what gets held into memory, right? So, I mean, clearly I have enough memory to hold 44 megabytes. The other factor is I have to consider is that I'm running OBS here, which takes up memory and is using graphics acceleration or something there. But I should be fine. So now that we have it downloaded, there's the lines to go ahead and run it. And so looking here, we see GPUs 1, so use 1 GPU. We could say all because we only have one. Net host, so use maybe networking host out to the internet. PWD for the current working directory, to the repository, to the models. And then here it is running the Triton server as a container, pulling it from probably Docker Hub here. And here are the model repositories. It's just specifying which model to load. So possibly there's more than one model that we downloaded, not just a single one in here. That's what I'm thinking. But then down below here we have server docs examples. Is that where we're supposed to be? That's where it put us. And we do have model repository here. And notice here it says model repository. So it's possible that there's a bunch of models. There is. So we have DenseNet, Inception. I don't know what all these are, but we're going to run DenseNet. Obviously does something with images. And we'll go ahead and hit enter. And so it's saying it can't find Triton because, of course, we have never used that image. So it's pulling that down from Docker Hub. So that's getting pulled down. So that's going good. We'll give it a second. All right, so right away it says unable to get power usage for GPU. So that doesn't necessarily mean a bad thing. It just means it can't get those metrics, but it's still successful for pulling the image. That is good. And so we ran that line. And so I'm assuming that it's running the way that we would normally check that, I guess. Oh, did we actually run the container? I thought we just did fetch model, right? Oh, okay, fair enough. So somewhere here on the left-hand side, we should have an extension for containers. Maybe I don't have it. Docker. I could have swore I had the Docker container. Maybe it's this one. Oh, it's not installed. I'm not sure where it went. It definitely was installed before. But the reason I want that is I want to see if it's running. So it's clearly running here. It's not stopped. That's really, really good. We're going to go ahead and make a new tab. And we'll bring this back open here. And so what I want to do here is you're sending an inference request. So in a separate console, launch the image client example from here. And so I'm guessing it's there, but it says workspace install, et cetera, et cetera. Is that really even there? Let's go back to here. It didn't open up the same directory, which is home, Andrew, CD sites, server, was it examples? Where did it go here? We had docs examples. It seems like a really strange way to navigate, but examples. I'm going to go model repository here into the DenseNet one. I'm just guessing. No, that's not it. Because here, I'm looking at the next step, right? It's a little bit hard to read. But we'll just take this command out here for a second, and we'll go up to here, and we'll make a new file here. And what I want to do is just get the lay of the land here. I just want to be able to see what I'm doing. Okay. And I'm just trying to make sense of what I'm looking at. This looks like, oh, it's another, is that another container? Okay, so it looks like what we're doing is we're just launching another container, or is that a different example? Launch the Triton container, sending an inference request. Launch the image client example from the NGC Triton SD container. So I think the second container here, it's just, I guess what they've done is whatever it's doing, it has the image, creating the image, and it's going to send it over the network, I guess. Right? Without opening up the container and looking at it, I'm not really sure. But I mean, that's what it looks like, right? Because they're saying one is running the server, one is sending the image, but we'll just do that. We'll send the image. It's going to download that. Again, it's probably just literally a container with an image in it. That's my guess. And so that will download it and then send it over to the Triton and make inference. What the API looks like, I don't know. When we're dealing with LLMs, a lot of them standardize based on the OpenAI standard. This isn't an LLM. This is just a smaller traditional model, I believe, like vision model. And so we'll see those capabilities here in just a moment. Okay. And so that's polling. And it looks like it sent a request and we have an image, right? So it's gone here. It says, so if it's working, there's the image and we have coffee mug, cup, and coffee pot. So that looks like what it did was it identified it. So I'm curious, like DenseNet, let's go back over to here, DenseNet. What is DenseNet? Well, I'm just curious, like DenseNet versus ResNet. ResNet adds features while DesNet concatenates features. Designed to train very deep models by addressing vanishing gradient. Okay. Oh, okay. So it's just dependent on your requirements here. So here, like limited GPU, training is priority, or you have limited training data. So I guess it's trade-offs in its approach. That's kind of interesting. Maybe I will retroactively go back and add DenseNet just because we've covered in this course. And we might want to just have a comparison. I'll have to do a little bit deeper research on that. It's not enough information for me. Why isn't DesNet adopted as extensive as ResNet? Yeah, we don't know. But anyway, the point is that we were able to perform our operation there, and that was really, really good. Was that the last one? That was the output. Yeah, and so not hard, folks. I'm going to go over to here. I'll just stop my container. So right-click, stop. And I'll see you in the next one, okay? Ciao, ciao. All right, I just wanted to take a moment to compare DenseNet versus ResNet. So they're both convolutional neural networks, and I found out that they actually all come from this ImageNet competition, which happened over multiple years. And so they had this one very specific thing or use case where they wanted to do image classification, which had to do with like detecting a dog and a plane and whatever. So that's whenever we look at like that ResNet example or DenseNet, they're always using those 5 images because that was the original use case. Obviously, these things can be retrained, not just for image classification, but for other things. But the ImageNet challenge was to solve things like vanishing gradients, degradation as layers increase, slow convergence. But what it told me was basically to make networks deeper and make training easier, and specifically with convolutional neural networks. Okay, and so we just compare these two. The key difference is speed and training. So ResNet is a lot faster to train, requires less memory, whereas DenseNet is slower. DenseNet is going to be a lot better for medical imaging or higher accuracy. ResNet's going to be for general vision, faster inference. These things can run on pretty lower tech, but there's a lot to unpack here with these two. Or just in this family. But again, I just wanted to make it very clear what the stuff was. I did notice that on the exam, they did talk about vanishing gradient points. And I'm trying to remember vanishing gradient point. And so I think in my GenAI Essentials course, I cover vanishing gradients. But basically the idea is that every time you are training, there's like those weights are changing, and eventually they might end up at 0, or they'll stall because there's only so much you can do as you change them. That's the best way I can explain them. But if you do see vanishing gradients, you don't have to really worry about that on your exam. Just always try to remember about the technical requirements, and these conceptual things aren't that as important in the exam. But anyway, I just want to compare DenseNet versus ResNet. I still want to see if we could train ResNet for something for fun. But yeah, we'll see you in the next one. Okay, ciao, ciao. All right, folks, here, let's take a look at Slurm. So Slurm is the Slurm Workload Manager, formerly known as the Simple Linux Unix Resource Manager. So that's probably where that name comes from. Or simply, Slurm is a free and open source job scheduler for Linux, Unix-like kernels used by many of the world's supercomputers and computer clusters. So if you know what a job scheduler is, you can think of it, basically it's a queue, right? Batch queuing. and traditionally used for HPC, so high performance computing style batch scheduling. And you'll notice here that there is, I'm trying to get my pen tool out here, but we have a bunch of different commands that we can control it. There is stuff that is controlling running it. It is backed by a database. And then it has to manage all the nodes over here. And so just tying this over to this, you can see that you have jobs, and within jobs, you have job steps, and then there's partitions, et cetera, et cetera. Not so important, but what's important is like, how do you create one? So you can create a Slurm file, and notice that we are defining like what we're using, how much we're using, the memory, the time, how we want it outputted, and then the actual script we want it to run. And then we need to schedule up using command. And there's a bunch of commands. There's way more than this. We can like look at a very specific thing in the queue or cancel the job, things like that. The reason we're learning about Slurm is that you might see the word Slurm in the exam. I did. And it's not that you need to know how to really do this, but you just need to distinguish, okay, Slurm is for job scheduling. It's open source. Okay. And that's that. All right. It's for Linux. All right, let's take a look here at the NVIDIA Base Command Manager. It is a cluster management software for AI and HPC at the edge, in the data center, and multi and hybrid cloud environments. There is a heads-up display of the interface, so you can see it's really, really nice. It streamlines cluster provisioning, workflow management, infrastructure monitoring. It ranges from 2 to 100 to 1,000 nodes. It supports Blackwell architecture, Rubin architecture, and other systems. So basically the new stuff. Enables orchestration with Kubernetes and Slurm. That is why we covered Slurm, because it can be managed via the NVIDIA Base Command Manager. Comes with UI, can be used with the NVIDIA DGX systems. Yeah, it's for rapid prototyping, multi-GPU training scripts, so you can run it via the BGM Managed Jupyter Labs to take advantage of scheduling authentication. For GPU quotas and automatic cleanup, eliminating infrastructure overhead while maintaining CUDA 12.6 and the NEMO framework access for prototyping. So what do I want you to remember about this is that it is a cluster management software, okay? And that it enables orchestration for with Kubernetes and Slurm. If you remember those two things, that'll be enough for you to know for the exam, okay? Again, this is an entry-level exam for NVIDIA, so we don't have to go super deep on these things. We just need to know what it is. And despite the technical terms they'll spin around, if you remember those two things, you'll get a point on your exam, okay? Let's take a look here at NVIDIA GPU Operator, and it uses the operator framework within Kubernetes to automate the management of all NVIDIA software components needed to provision your GPUs. You can find it over here. This is going to provision things like NVIDIA drivers, Kubernetes device plugins for GPUs, automatic node labeling, DCGM base monitoring, and others. Down below here, we are using Helm to add it. And the reason I added that piece of code there was because on my exam, when it was asking about NVIDIA GPU Operator, it was talking about like, how do you get it installed? You use Helm, right? So as it says, it's very straightforward. It makes it really easy for you to start using your NVIDIA GPUs on Kubernetes when you install this thing, okay? That is what you need to know. Ciao, ciao. All right, let's take a look here at NVIDIA Data Center GPU Manager, also known as DCGM, and you might actually see that initialism on the exam, so make sure you know what it stands for. It is a daemon that allows users to monitor NVIDIA Data Center GPUs. So it includes active health monitoring, comprehensive diagnostics, system alerts, and governance policies. DCGM integrates into Kubernetes ecosystems, utilizing multiple native API bindings, so C, Python, and Go. But you just have to remember, it's a daemon. It's a program that is running to monitor your GPUs. Pretty straightforward, okay? Hey folks, we are taking a look at H100, and this piece of hardware comes in two flavors, which we will cover here in just a moment, and it's using the NVIDIA Hopper architecture, which we will dive into. One thing that I do need to point out is that these H100s are probably going to be in use for quite a while, like to the end of the decade, and this has to do with the fact that there is, at least at this moment, there is a shortage of memory and things like that. And this is obviously being caused by NVIDIA because of their large back order. And so I imagine these H100s are going to be kicking around for quite a while. And so not just outside of the fact that this exam heavily relies on their data sheets to pass it, yeah, it's just good to know these things, because you're going to probably, if you're going to see anything in the wild, it's probably going to be H100s. Okay, but let's talk about the two variants. The other thing that's confusing is the exam won't always tell you if they're talking about the SXM or the NLV, but you can NVL, whatever the other acronym is for NVIDIA link. But the thing is that you basically can deduce it based on some key values. And so we'll pay close attention to these key values, and that should help you deduce it. But I kind of found it frustrating they wouldn't specify which one it was. So the first one is the H100 SXM. So that stands for Server PCI Express Module. This thing is faster, and it does use NVLink. The key thing you want to remember here, like if you want to distinguish these two, is this one has 900 gigabytes and the other one's slower. Okay, but this one has less memory, whereas the other one has more memory. Its TDP is 700 watts. That means how much heat it will generate at max. So that's what you have to target for cooling this device. You might get a question about cooling, right? And it hinges on knowing that this thing is 700 TDP. So that's something you need to remember. There might be a question about throughput, GPU to GPU communication, and how much data is being sent between them. So remembering that it's 900 gigabytes per second, that's how much you got. You have to factor that in. There could be a question that says 1689 6 cores. It's talking about usage. And then the answer is use the H100, right? Because you can map that value over to here. Tensor cores don't come up much, but I figured I'd put that in there anyway, because you should know how many tensor cores are in there. Knowing how much memory there is very important, because imagine you have a model. If you need to load the model on a single card and the model is over 80 gigabytes, it won't fit on it, right? And then you have to distribute it across. You have to need more than one card. Or if you are doing training, so if you're doing inference, it's the size of the model that needs to be held in memory. If it's training, you need 2, 3, 4 times the amount of memory, so you have to factor that in. Okay, you might even see the speed here, the terabytes per second. So you need to remember the data sheet. And it will make it really easy to make the right choice. Over here, we have the NVL. Notice that they were shipped basically around the same time. This one's shipped, this one's shupped. I like that. That's a funny spelling mistake. But this one's much lower in terms of how much heat it's producing. But it's obviously going a lot slower. It has fewer cores. And then the big trade-off here is that it has a lot more memory. So it's important to remember how much memory there is, okay? And you have to deduce it based on those other values. So CUDA cores excel at massively parallel operations. So the more cores you have, the more parallelization you can do. Parallel operations will perform well on H100s compared to CPUs. I keep repeating this in the course because if you remember parallel operations, think GPUs, think CUDA cores, okay? And because that question came up a lot, was choosing between GPUs or CUDA cores and CPUs, okay? But there you go. All right, so we did cover what a GPU is, and we did do a comparison against CPUs, but I just want to iterate it again with another graphic with a little bit different information, just so it sticks. And so here on the left-hand side, we have a representation of a CPU and then a GPU. And you can see the green parts is the processing power. And it clearly looks like the GPU can do a lot more. So CPUs, besides just processing, needs to reserve die area for big caches, controls, units, and things like that. We're seeing that. So we see all the blue stuff, the purple stuff, the yellow stuff, right? There's a lot more going on than just processing. Okay, GPUs dedicate most of their transistors to data processing. As you can see, this big area is processing, okay? Down below, what's important to understand is also just the way the threading works, or how it processes tasks. So CPU processors work on minimizing latencies within each thread. Okay, so down below, like here it says computational thread. And so here is an example of a thread. All right, and notice everything is stacked back to back to back to back to back to back to back. All right, so it's sequentially running, whereas when you have GPUs, they are running parallel to each other, right? And so the idea here is that GPUs hide the instruction memory latencies with computation. So the idea is that, yes, some of these things are slower or faster than others, but the idea is you're not waiting in line for stuff, okay? And so that's the clear difference there, and hopefully that's good, okay? All right, so I just want to quickly show you where the datasheet is. So here I'm on the page for NVIDIA H1 GPUs. If we scroll on down, it says datasheet. And if you click through that, you can see all the specs here. So I obviously wasn't showing you everything, but this is worth your read. It's not really that long, but if you can remember those key things that I point out, like the memory usage and the memory bandwidth, we don't care about decoders, that doesn't matter, but like the interconnect information, things like that, then you are going to be in good shape. Down below, we even have server options. So you can see it's between 4 and 8 GPUs or 1 and 8 GPUs, because there could be a question in the exam that's talking about, the mount that you're doing it in. And so here, notice it's 4 or 8, right? It's not 1 or 8, it's 4 or 8. And so that's one of the possible configurations, right? So, all things you need to remember. If you can remember that stuff for your exam, this is something I would go before the exam and just kind of like reload your brain up, and you'll do really, really well. I mean, we do cover MIGs in the course, but like, I don't think you need to know how many MIGs. Like, this is the subdivisions of taking a GPU and splitting it into smaller ones. But it's nice to know that you can split it up into 7 and how much you can split it up into. But yeah, and basically everything has a data sheet. So like, we have H100 here, but H100 is obviously not the latest. So if we go over to here and we go to wherever we are here, maybe go back to data center. Can I do it this way? Let's see. I'm just trying to look at the resources. Their pages are not easy to navigate. Okay, and so I'm just trying to find where all of their products are. I've seen it here earlier. We'll maybe go shop. That's not helpful. Products. Data center, DGX platform, and we go into ecosystem. Nope. I knew where this stuff was before. I'm so sorry, folks. Resources. Because here they have like a list of all the DGX systems, and that gives you kind of an idea of what's going to be used underneath. Just give me 2 seconds. I'll find it. Actually, you know what? It's probably in the store here. If we go to the store, data center. Already had it open. Yeah, there we go. So we'll go to GPUs. And so like we have H200s, H200 NVLs, L40s. I'm just trying to show you there's other things besides H100s. Okay. Go NVIDIA platforms. It's a lot better to look at the from this perspective, because generally these graphics cards, and we'll talk about this in a separate slide, but you're basically buying DGX and then those have graphics cards in them. And so here it's B300, so that's Blackwell, and it's the Blackwell 300 edition, right? So there's clearly a lot newer stuff than H100s, but that's what the exam focuses on. And it just seems like H100 is like a middle ground for having a good place to reference things, okay? But there you go. All right, let's take a look at NVIDIA Hopper architecture. So that's the thing that is powering H100s. And they have a bunch of things here on the right-hand side, so let's dive into it. So the first thing, and most important thing, is that transformer engine, which you are seeing there on the right-hand side. If you know anything about LLMs, is that they use the transformer architecture. And so obviously having a transformer engine is going to make this thing super optimal for large language models. The NVIDIA Hopper architecture supports NVLink, NVSwitch support. As we saw, it was listed under the H100. We have NVIDIA confidential computing. We have second generation multi-instance GPUs or MIGs. We saw that in the datasheet that you could split them up into 7, the H100s. We have DPX instructions, it's just the way to talk to it. And then obviously there are tensor cores included here. So tensor cores can do specific things like matrix multiplications very quickly. So it's a specialization of something they can do in there. For every transformer layer, this is what's happening. We have a query key value projection of 3 matrix multiplications, attention score computation of a matrix multiplication, attention output, feed forward networks. So a lot of operations that are occurring for large language models, and it's leveraging those tensor cores along inside of that transformer engine. Because if you're looking up here, like look at the graphic here, we are taking just these 2 parts here, and we're going to this part, and you can see right, that it's utilizing those tensor cores, and the transformer engine's right here. I don't know why I pointed up here because it's actually right here. And so that should be pretty darn clear. So just to really sum it up, because again, we don't need to know this at a super deep level, but transformer engine plus tensor cores equals really good at running LLMs, okay? But there you go. Hey folks, we're taking a look at the transformer architecture, which was developed by researchers at Google. That is the way that NLPs work using multi-head attention and positional encoding. This is actually the slide that I took from my GenAI Essentials course. And it's not like super important to know, but you should know that LLMs are using the transformer architecture underneath. And so there is this pattern that is utilized here, and it's made up of 2 parts. The first is the encoder, so it reads and understands the input text. It's like a smart system that goes through everything it's been taught and picks up on the meaning of words and how they're used in different contexts. And the second part is the decoder. Based on what the encoder has learned, this part generates new pieces of text. It's like a skilled writer that can make up sentences that flow well and make sense. Okay, so there are those 2 parts. And the way we're anchoring this to this NVIDIA certification is the fact that you look at the architecture we just looked at, the was Hopper architecture. It was Hopper, right? Hopper. And it has that transformer engine. And so the idea is that you're seeing that this thing maps to that thing, okay? And so if you remember that, then you are in good shape. Oh, yes, and we're just pointing to everything here. So it says multi-head attention, so it's pointing to where that is, where the positional encoding is. I'm not going to get into it in this course as... we don't need to cover it in detail in this one, but just know what transformer architecture is. All right, I know we just keep talking about the transformer engine, saying the same thing over and over again, but I have to make it really clear because this will help you on your exam what it does. The NVIDIA transformer engine is designed to run transformer models, based on the transformer architecture. LLMs are built on top of the transformer architecture. And this transformer engine uses both 8-bit and 16-bit floating point precision. That is what it likes to run. Okay, I really should have highlighted this part here, like with yellow or red or whatever, because this will show up on your exam. When you have a model and you're going to run an H100s, what does the model need to be? 8-bit floating point precision or 16 float point precision, okay? Remember those 2 things, you will be in good shape for your exam. So I kept coming across Grace Hopper and it was confusing me, so I figured we should bring it up because that can get confusing. So Hopper is NVIDIA's GPU architecture, so what you'd find in H100, and Grace Hopper refers to a combined module, aka superchip, like the GH200, that pairs the Grace CPU, so an ARM-based CPU from NVIDIA, with the Hopper GPU. So that's pretty much it. The other thing is that they're connected via high bandwidth, low latency NVLink here. And if you look at the graphic down below, I think it's pretty clear what's going on here. We have the CPU, we have the GPU, you have your NVLink, okay? So that's all it is, okay? Hey folks, let's take a look at thermal design power, also known as TDP. We already talked about this earlier, but I didn't give it enough attention. I want to make sure you fully understand it. So TDP is the specification that indicates the maximum amount of heat a component can take on. And the value is measured in watts and represents the amount of heat that the cooling system must be able to dissipate to keep the component operating within the safe temperature limits. So we already saw before for the H100 SXM, it is 700 watts. And then for the H100 NVL, it's up to 350 to 400 watts. So yeah, you will encounter this on your exam. So just make sure you know what it is. And, if something says the cooling system has to disperse a certain amount, that's important for us to know, right? Let us take a look at a closed loop liquid cooling system. So when cooling a CPU or GPU in a liquid cooling system, a closed loop one in particular, you're pumping a liquid through a cold plate, and the chip you want to cool will sit on this cold plate and provide direct to chip cooling. And I noticed I missed the T there. As you know me, I'm always missing letters. But this is a term that you might see on your exam. You might not. But direct to chip, you should think closed loop liquid system. And the liquid itself, it could be water, it could be gel, it could be some kind of thing. There's all sorts of things. So it's not necessarily water, okay? And so here are just two examples I found online, and they look very similar, but they both have a cold plate. So this one says water-cooled cold plate. So this one's obviously using water. This one, it doesn't indicate. And here you see the electric module. So it's describing here the GPU or CPU. And then here we have cold plate heat source. Here it's describing, again, that chip. And so, yeah, there you go. Not too complicated, right? All right, so let's talk about direct to chip cooling or direct liquid cooling. And you might use a piece of hardware like CoolIT, like the CH1500, and its job is to try to hold that rack or rack of servers to a temperature of 4 Celsius, where we have, if you're using this for your primary workload, 1,100 liters per minute, or secondary is less. Here you can see that it can cool quite a few machines. So here we have a 72 rack, 72 graphics cards, those Grace, Grace Blackwell graphics cards. So a lot of graphics cards there that it can cool. So very expensive system, but obviously very, very capable. So when you're cooling 700 watts TDP GPUs, liquid cooling is preferred and is often the only option over air cooling. We didn't really cover air cooling, but when we're talking about AI data centers, it's just not going to cut it. So if you get an option on your exam that's asking about like air cooling or whatever, just go with direct liquid cooling. So direct to chip or closed loop or liquid cooling, especially if you have like an H100. I know we're not showing H100 here, but we have an H100 and it's the SXM and it has a 700 watt TDP, then you need liquid cooling, okay? And that's your answer. All right, so I don't have much to say on this because there's not a whole lot on the exam, but I just wanted to cover a few terms about power density approaches. So that's how you can cool your system, whether it's liquid cooling or air cooling or whatever. So what is liquid cooling? So it will reduce the heat, but not the power consumption, okay? It reduces heat, but not power consumption. So that is something that is very clear to make a note of. What would be an example of that? A closed loop system where it's it's cooling directly to the GPU, right? But does not reduce your power consumption. The reason I keep repeating that is that you might get a trick question where you think that liquid cooling is going to reduce your power consumption, and it just doesn't. What about power supplies? That's the thing that supplies power. Well, it will reduce heat, but not power consumption. Again, it will reduce heat, but not power consumption. So just repeating that. Let's talk about what an average rack would consume, just so you have an idea of how much energy is being utilized. So in 2011, an average rack consumed about 2.4 kilowatts. In 2026, an AI rack can consume 300 kilowatts. And then if we're talking about in the future, we have a forecast of 1,000 kilowatts. So you can see that things are going up insanely fast, just insanely fast, okay? And just speaking of liquid cooling, it may reduce heat, but it will not reduce electricity consumption and is not a solution to increase capacity per rack. So what am I trying to get across? It will not reduce power consumption. So there you go. All right, folks, let's take a look at power density planning. So imagine you want to deploy 64 100 HPUs. You must be rich. You got a lot of money if you got that many H100s. But it's saying 700 watt TDP. So which is it, SXM or NLM or whatever the other one is? It's going to be SXM because that's the one with the higher usage. Okay, the rack has 15 kilowatts per rack. How many racks do you need? So if you have 64 GPUs times its maximum TDP, that's how much wattage we're going to need. And so we turn it into kilowatts by just moving it over. And so we get 44.8, right? And so if you have 44.8 divided by 15 per rack of how much we can put into a rack, we need 3 racks per minimum. Okay, but that math can be hard to do on the fly. So if you need to simplify it, simplify it. So we have 64, and we'll just make it a 7 here. That will give us 448. We'll move it over, so it becomes 450, rounding it up. And then when we shift it over, it just becomes 45. 45 divided by 15. And if you want to round down or round to the closest, we have 3 racks. And so that's going to kind of help you figure on the fly. I actually know how to count in 64s all the way up to 448. If you are in tech, you should know how to count 2, 4, 6, 8, 16, 32, 64, or in the power 64, things like that. So if you don't know that, you have that as a blind side, maybe learn how to count up to power 64s up to 8, I think is very, very useful. But you know, if we round it up to 4, because it said between 3 and 4 racks, and we do 64 divided by 4, we can fit 16 GPUs per rack. Okay, but besides that, we have to consider you need to have overhead for cooling and power distribution, right? That's why we went from 3 to 4 racks here. Okay, you have to consider what the configurations are. So 8 GPU servers are common for the DGX H100 baseline. When we looked at it, remember it depends on whether it's SXM or LVM. I always forget the initialism for that one for NVIDIA Link, but remember it said between 4 and 8 GPUs for SXM, and for the NVIDIA Link one, it says between 1 and 8, right? So let's err on higher side. We'll say 8 because that's generally what people want. And so here we have 1 to 2 servers per rack, so 8 to 16 GPUs per rack. And so you should plan with an overhead of 30%, right? And again, that's why we brought in another rack here, so that's why it's okay. So having a single server, 8 GPU per rack, makes sense since you are installing 8 per server, okay? Liquid cooling may reduce heat, but it will not reduce electricity. I keep repeating this constantly because this will help you on your exam. It will not reduce the electricity usage. This is not a solution to increase capacity per unit. Okay, it's not going to deliver more electricity. That's a separate thing. All right, let's take a look at NVIDIA DGX, which stands for Deep GPU Acceleration. This is a series of servers and in a rack mount format, providing GPUs for general purpose computing for enterprises. I don't know why there's an I on the end of there. That's probably just a mistake, as that's me per usual. So here we have a DGX SuperPod, which is a full stack data center platform. So it's not just the compute, but everything around it. And that probably also includes support and other stuff like that. And then here we have the NVIDIA DGX, and this one is the H200. Honestly, these boxes all look the same. So if you have an H100 and H200 DGX, they'll have the same exterior, but what's inside may be different. So the example of the H200, it has 8 times H2 GPUs, which comes with 4 NVIDIA NV switches with 10 times NVIDIA Connect X7s, and these have dual Intel Xeon Platinum processors of the 8480C, which we keep seeing that. And actually on the exam, I think I got a question about it, so that's why I'm emphasizing it. And there it has 30 terabytes of NVMe SSD. Never had any questions on the exam about like limits of storage. I mean, there was stuff about storage, but not about the limits of how much we need. So never had a question on that. But yeah, that's the NVIDIA DGX. So just understand that that's their full stack data center platform. It's like you buying into their system, so you can just drop it in and go, okay? All All right, let's take a look at the NVIDIA DGX H100, as this is most likely to appear on the exam. And of course, there are newer things. There's Blackwell. There's obviously newer versions of even this Hopper technology. So, just consider that. But let's continue on here. So what's inside one of these boxes? Well, we have 8 of these H100 GPUs. We have 18 NVLink connections per GPU. We have 900 gigabytes per second of bidirectional GPU to GPU bandwidth. I think this indicates that this is using SMX. You remember there's 2 types of H100s, because if it's 900 gigabytes per second, I think we saw that earlier in the data sheet. It has 4 NVIDIA NV switches. We have 7.2 terabytes per second of bidirectional GPU to GPU bandwidth with 10 times ConnectX 7s. And they have dual Intel Xeon Platinum 8480C processors with 112 cores total and 2 terabytes. I'm emphasizing that because you might get questions on the exam about CPU usage. And if you know that there are CPUs within these things, then it comes down to the amount of cores and what you can do with them. And so that's why I'm making emphasis of that here. So that is fine. Also notice that I'm making strong emphasis of GPU to GPU bidirectional information. So these 2 values are important as well, as those might appear on the exam about how much can move between systems. If you know the data sheets of the H100, of the DGX H100, you're going to do really well on the exam. That's why I keep repeating these values, just so do you remember them, okay? So NVIDIA DGX H100 systems generally cost between $300,000 to $450,000 per unit. So yeah, think about how much that is, right? It's expensive. At the time of 2026 Q1, that's what it is. And then down below here, if we're talking about petaflops of how much it can process, we have a total of 32 petaflops. Sometimes you want to measure in that amount. Notice that it's saying FP8. Remember that there are 2 different precisions. We have FP8 and FP16. Just depends on what you need to do. So maybe it's 16, that's a different value. We're not going to really get into that, but yeah, this is the NVIDIA DGX H100, and just, consider there are a bunch of them in there, okay? Let us take a look at the dual Xeon Platinum 8480C. This appears in the H100, but I think it appears in other things like the H200. So I think this one is going to appear more often than you think. But let's go ahead and cover it. So it has a total cores of 56, a total threads of 212. It has a TDP, so how hot it will get is 350 watts. The recommended customer price is $10,000. But this is confusing because down below, notice we have an Intel Xeon Platinum where it's only $1,299, but maybe because it's bidding that it can go up to $10,000. So they're kind of like trying to trick you here on eBay, because this isn't something you would really buy, like as a consumer. This is something that you, like, I guess you consider like OEM or something that you'd buy indirect, right? It's a 4th generation Intel Xeon Scalable processor. Again, you might just remember it's 4th generation, as that might come up. It was launched in 2023. And the thing is that the numbers here are a little bit too low. We saw earlier that it was actually like double, or like 112 plus 244. And so maybe dual is implying that it's doubling up. So 112 actually becomes 244 threads. That would make more sense for hyper-threading, okay? And the amount of cores is useful for pre-processing tasks. So this is the stuff preparing it for the actual, like let's say you have the LLM, it's whatever it has to do before it actually runs the LLM. And so it's important to know that, it's not going to be the same level of parallelization of running those computational mathematical tasks, but these things are more complex tasks of data manipulation and things like that. And we don't need as many cores, but we still need a certain amount of cores to do stuff. And so just remember that number, okay? The 112 to 224 threads, and that these CPUs are still being utilized for the AI stuff, or it's just for the pre-processing tasks. All All right, let's take a look at NVIDIA DGX scalable units. So DGX SuperPOD architecture is a combination of DGX systems, InfiniBand, and Ethernet networking management nodes, and storage. So this represents the rack layout of a DGX SuperPOD, or single scalable unit, or SU. You might hear that term SU on your exam. And so you can see it's like a visual representation of racks. So you have your DGX H100s, your PDUs on top. So nothing super exciting. So let's just talk about InfiniBand for a second. So InfiniBand HDR or NDR, that is the generation of InfiniBand which determines the speed of that networking fabric. Utilizing with GPU direct RDMA will provide the low latency for GPU to GPU communication between stacks of the same server and other multiple stacks. I know we haven't covered InfiniBand or GPU direct RDMA. We are going to, but you're going to hear me repeat this again and again and again and again. InfiniBand with NDR plus GPU direct RDMA is going to get you low latency for GPU to GPU communication. Remember that, you'll be in good shape. All right, let's take a look at the NVIDIA H100 GPUs. And you might say, Andrew, didn't we cover this already? Yes, we did. We covered it once, we covered it twice, and we'll cover it thrice because you need to know the H100 really well for this exam, and you should just know this one in particular quite well. So the H100 features Hopper architecture. That's why we have that H in front of it. And so it is paired with that Grace CPU and the Hopper GPU. Okay, so Grace Hopper super chip, basically, it claims the 30 times speed up for large language models because it has that transformer engine. We have 900 gigabytes of bandwidth, or 7 times faster than PCIe Generation 5. Remember, the 900 is indicating the SMX. I think that's the initialization. Might be saying it wrong, but the one that starts with S, that's the one there. It has 4th generation tensor cores because we have a 4th generation, chip. Okay, 4th generation NVLink, NDR quantum InfiniBand networking. We haven't covered InfiniBand yet, but notice that it says NDR because there's different generations of InfiniBand. And the one we need to know is the one that it can utilize. And so NDR is the one it can utilize, and that's what we care about. It has a dedicated transformer engine. This is used to solve trillion parameter language models. There's the graphic. I don't know which one it is. I couldn't tell you which one it is, but there's an image of one. And there's a simple representation of the transformer engine, which we already looked at. And then we have the H100 NVL. So remember, there's the SXL, M or whatever the first one is. And the other one here is the NVL, which here's just showing its network through PCIe NVLink in 188 gigabytes. And so this is the one that has more memory. I'm just showing you the total when you're using the NVLM, what the total is. And that's what I wanted to highlight there. But there you go. All right, this is a term you probably kept seeing, which was ConnectX. So let's talk about what it is. So NVIDIA Mellanox ConnectX. And the reason it says Mellanox is that this was a product or company that was bought out by NVIDIA. So that's why we have that here. But you can think of it just as ConnectX, or NVIDIA ConnectX is a series of high-performance network interface cards, so NICs or smart NICs, which provide up to 400 gigabytes per second of Ethernet or InfiniBand connectivity for data centers, cloud, AI, and storage. And we will talk about InfiniBand at some point, but not right now. So here you have different increments of Ethernet network adapters. So you have 10, 25, 40, 50, 100, 200, or 400 gigabytes, right? So a lot of different sizes here, just to give you an idea of the range of what you can have. And so it is on the upper range. But let's take a look at some of the products they have. So they have ConnectX-9 Super NIC, which gives you 1.6 terabytes per second. And this is using PCIe Generation 6 with 48 lanes. Not in this course, but in one of my courses, I know I talk about what exactly PCIe is. And PCIe is different generations. And within a generation, there's different sizes of the lanes. And so the lanes is like the actual thing here. If I get my pen tool out, this thing here is the size of it, right? And in a generation, they can have multiple lane sizes. So then here we have the ConnectX-8 Super NIC, which is 800 gigabytes per second. So it's less, like half. It seems like whenever they have a new generation, they try to double it. That's not necessarily always the case, but generally that's what I've noticed. And so here it's 800 gigabytes per second. It's still using generation 6, but notice it's using 48 lanes as well. Then we're going to Bluefield 3 SuperNIC. Okay, and so here we have 400 gigabytes per second. This is using generation 5 with 32 lanes. And this is a DPU without the processing power. So we'll talk about DPU in a separate thing. In fact, the next slide is. But this is just the NIC side of it. There's no DPU in this, okay? But yeah, this is ConnectX, and just know that it's a smart NIC that is made by NVIDIA, okay? And it has really fast throughput. Let's take a look at the NVIDIA Bluefield platform. And before we can talk about that, we need to know what is a DPU. A DPU is a data processing unit. It's a programmable computer processor that is tightly integrated with a general purpose CPU with network interface hardware. And this is a term that was coined by NVIDIA if you hear of a DPU. So let's take a look at the Bluefield 4 DPU, which provides 800 gigabytes per second. Okay, so it has an inference context memory storage platform. And so this is great for AI native storage for faster long-term and short-term memory. Remember that it's called a data processing unit, right? So what data do we need to process? So here it is long-term and short-term memory. We have the NVIDIA Rubin cluster level key value cache. So that's how it's storing the data, is via key value stash. Think of like Redis. You know, I'm not saying that's what it is, but think of like Redis as an example. Here we have the Bluefield 3 DPU. And this is more like what you might encounter on the exam, but we have the fourth one here. Notice that it doubles. So we have 400, now we have 800, right? And this uses the ARM Hercules CPU cores. I believe the reason I highlighted this is because I saw it on the exam. And so I just wanted to anchor the fact that the Bluefield 3 DPU is using ARM Hercules. And also notice that it's an ARM architecture, not x86. So it has built-in security, distributed network generation firewalls, IDS, IPS, root of trust, microsegmentation, DDoS protection, MACsec, IPsec, TLS, data in motion encryption. You're supposed to know a bunch of data offering, or like security offerings, and if you generally know this list of stuff, especially for the Bluefield thing, then this will probably help you score most of your points for the security one. But IPsec seemed to come up a lot, so I just highlighted IPsec. I don't know if I made a separate slide of what IPsec is, but just know that IPsec is what really, really matters. We have Bluefield 3 SuperNIC. So notice that we've dropped the DPU name. It's just SuperNIC. It's still 400 gigabytes per second, but this is basically Bluefield 3 without the compute, without the data processing part of it, okay? So there you go. Let us take a look at NVM Express over Fabrics. Okay, so what is NVMe? This means Non-Volatile Memory Express. So NVMe is a high-performance storage protocol designed for solid-state drives that connects directly to the CPU via the PCIe bus. So the SSD is somewhere in there, and the PCIe is this connection here on the end. It looks really strange because it looks almost like RAM. The RAM would be on the bottom here. They'd have the thing on the end here. But I know that some people get this mixed up and they think they're looking at RAM. And we're talking about like high performance storage, which people might think is RAM. But RAM is not the case, as it's not persistent. This is persistent storage SSD. So let's try not to get that mixed up here, even though they look visually similar. And so you might start anchoring that information there. But what is NVMe? So this is NVMe. So it's using the message-based commands for this to transfer data between a host computer and the target solid-state storage device over the system, over network, such as Ethernet, fiber channel, or InfiniBand. InfiniBand is super, super fast, and we will talk about it separately. But this is the way that we do it, is through NVMe, so over fabrics. Tunneling NVM commands through RDMA fabrics provides a high throughput and low latency thing. You're going to notice RDMA paired a lot with InfiniBand, and there's good reason for that, and we will talk about that when we reach it. The reason we covered this is because we want to talk a bit more about Bluefield storage acceleration, and it's going to mention this term NVMe over fabrics. We want to make sure we know what this is before we talk about that, okay? So if there's something that we should know about Bluefield, it's the storage acceleration that it has. So Bluefield DPUs accelerate storage by offloading via the NVMe OF protocol over fabrics with the RDMA operations and storage networking from the host CPUs to the DPU's ARM cores. So take it off the host CPUs onto the DPU ARM's cores. And this is going to free up CPU resources for compute-intensive AI workloads while still delivering low latency, high throughput storage access. And so I'm trying to carefully look at this diagram here so we can make sense of it. But notice here we have the host x86, okay, and see the PCIe down below here. That's the PCIe connection. And the idea here is that it's going to offload into the ARM here and then go out into, I think, no, the DPU unit can go around here, so it doesn't necessarily have to go this way. And then it's going through here through the network, okay? So anyway, there you go. The thing that you need to know about the storage accounts is that it frees up CPU resources for compute-intensive AI workloads, okay? Let's take a look here at NVIDIA Collective Communication Library, NCCL, also pronounced nickel. What's really interesting about NVIDIA is that they have unusual names, but they also want you to pronounce them a certain way. I do appreciate that they actually tell us, but honestly, you know, as a user, if it's NCCL, I'd rather say NCCL. So NCCL allows you to network multiple GPUs together without the need of tuning specific hardware configurations. And so the idea is that it is great for distributed training or real-time inference. It has automatic topology detection. It has a streamlined C-based API, and it can be installed via compiled from source NVIDIA HPC SDKs and precompiled binaries. So again, NCCL allows you to network multiple GPUs together, right? That's the key thing. So if you're using NCCL, you are doing multi-GPU or multi-node, okay? I do a better job covering PCIe in another course. I don't remember which one, but I'm just going to briefly cover it here because we keep mentioning it. And just in case it hasn't sunken in yet, PCIe are these interfaces for you plugging stuff into your computer. So if you've ever built your own computer, custom thing, you've plugged it into PCIe, and PCIe has different sizes of lanes, right? And so the purpose of PCIe is to allow you to directly connect to the computer's motherboard. And so all these things can talk to each other. And again, I'm just reiterating because you're going to hear about PCIe when we talk about NVLink. And there you go, okay? Let's take a look at NVLink and NVSwitch. So NVLink is a high-speed direct GPU to GPU and CPU to CPU interconnect technology designed to overcome the bandwidth bottlenecks of traditional PCIEs, providing up to 900 gigabytes or 1.8 terabytes bandwidth. Okay, so NVIDIA does not traverse PCIe at all, but it has its own special connection to do so. And the reason I just call this out is because these things get plugged into the PCI port, right? But they also have their own connection. Then we have NVSwitch. So this is a specialized high-speed networking technology enabling all-to-all GPU to GPU communication at maximum NVLink speeds within a single server or node. And the one we're looking at here is the HGX H200 8 GPU with 4 NVIDIA NSwitches devices. So you're not just seeing the NVSwitch, because the NVSwitch is right there on the front. You see it highlighted in green, but you can see that it has 8 graphics cards in there. The NVLink NVSwitch operates only within a single node. So a node is your computer, your box, that thing. So they're all only for that thing. And they're going to network it in. So we have 1, 2, 3, 4, 5, 6, 7, 8. Then notice there's 4 switches, and they're making connections all over the place. And so even though it's on the end here in the illustration, they show it in the middle. So NVLink is physically plugged into the PCIe, but NVLink has its own physical link, so it completely skips PCI for faster throughput. So I'm looking here, I'm going, okay, somewhere here it plugs in, and because I don't have these, I can't tell you where they are, but maybe it's like this over here, or there's some connection here, but the point is that it's connecting some other way. Let's talk about configuration of NVLink. And so it's important to maybe know the different generations or numbers so that we have an idea of how many links we can establish. The links is, I believe, the connections we see here, like the connections over here. Okay. And so it's going to limit, I guess, how many GPUs you have within a node. But for NVLink, we have a 20 gigabyte transfer rate with 4 links. For 2, it's 25 with 8. For NVLink, it's 3 with 50 and 12. For 4, and that's what we're using with H100s, we have 50 for 18. So if we come back over to here, I don't know how it works, but like there's 8 of them, and 8 becomes 18 between the way that they are crisscrossing like that. Who's ever good at math, you tell me how that works. For Blackwell, which is on NVLink 5.0, same number, but the transfer rate is much higher. So if you have an 8 GPU DGX H100, you will get 18 links with 50 bidirectional transfers with 25 per direction. Understand that if you have a bidirectional thing, cut it in half to figure out per direction. That could matter on the exam. But that bidirectional thing, just watch out for that, okay? But there you go. All right, let's take a look here at InfiniBand. We keep talking about InfiniBand, like mentioning it, but we never really explain it. So let's explain it now. So InfiniBand is a computer networking standard used for high-performance computing with very high throughput and very low latency. InfiniBand uses switch fabric network technology, and we have this big grid here of the different generations or different versions of InfiniBand over the years. And they have those funny little initialisms, but they actually do have names. It started out logical originally, like single, double, quad, but then they couldn't go with that naming convention anymore, so we get high and next. The ones that we really care about is HDR and NDR, because that's what's going to appear in your exam, mostly NDR, okay? That's what H100s are using, and so that's what we really want to focus on. Look at the right-hand side where we see adapter latency. It says, make note, I wrote that, make note, IB starts at 5 microseconds. Okay, so if you get a question that's like, hey, you need to factor in latency, and they're talking about 10 microseconds, if you're using InfiniBand, it's even the oldest one, it's under, right away, it's under 10 microseconds. And then we talk about HDR and NDR, look how slow it is. We have HDR and NDR, those are the ones that we're going to be caring about, even maybe XDR, but we have under a microsecond, so half a microsecond, even less. And so, we need to factor that stuff in. With NDR, I would say think 1 to 2 microseconds, but there's a footnote there for a reason. I can't remember exactly as to why, but I think that it's safer to just think 1 to 2 microseconds. But apparently, it's super, 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 super fast. Okay, or like reduced latency. A very reduced latency is what I should say. Also, look at the throughput. So you can just see here the throughput over here. And again, it depends on what configuration you're using, but we have very, very high gigabit throughput. Okay, let's talk about InfiniBand cables. So InfiniBand cables come in several speed grades, and depending on what cables you have installed is going to determine your actual throughput. So just because you have NDR, you need to know what cables you're using. If it's single lane, if it's dual, because look, it goes from 200 to 400, literally doubles. It goes to 800, right? Same thing with XDR. It only has 2. It has a 4 lane and an 8 lane. And so what's installed is going to determine your actual speed. So even if you think you know NDR, you also have to think, is it NDR 200? Right? So if you are using the wrong speed of cables, you'll not get the expected bandwidth. I think I had a question about this where it was saying like everything looked fine, everything was set up, we're using InfiniBand, and we're getting half our performance. And it turns out the answer was they're using, instead of using NDR 400, they're using NDR 200. And so it wasn't that the hardware and the mesh couldn't handle a faster speed. It's like if you have the wrong cables, it's not going to help you. But here it says DGX SuperPod with Connect 7 using NDR 200 instead of NDR 400. So that's an example of like, oh, you should be using NDR 400, but you're using NDR 200, right? So, again, look at those things in the data sheet and pay close attention to that. But yeah, there you go. So RDMA is remote direct memory access that lets one machine read from another machine's memory, write directly into another machine's memory without involving the remote CPU with very low latency and very high throughput. What are we talking about here? GPU to GPU memory communication, right? GPU to GPU memory communication. And so you'll often hear InfiniBand along with RDMA, as if sometimes InfiniBand does not necessarily go with RDMA, but InfiniBand is a networking standard or fabric and defines cables, switches, signals, and protocols. RDMA is a NIC that supports RDMA, so special hardware for RDMA. It has driver support. It has libraries to utilize RDMA, so basically the software to utilize it. And RDMA is almost never used without InfiniBand. So treat it as always InfiniBand plus RDMA, and you'll have a really easy time, okay? Let's take a look here at ROC, or however you want to pronounce it. But it stands for RDMA over Coveraged Ethernet. It is a network protocol which allows remote direct memory access over the Ethernet network. So RDMA over Ethernet, right? There are multiple versions of ROC. We have version 1, version 2. Version 1 is an Ethernet link layer protocol, whereas version 2 is an internet layer protocol. So with ROC, again, I don't know how to pronounce it, so I'm just saying ROC supports RDMA, and it can be used, I mean, it has to support it, it's right in the name, right? But it can be used with standard TCP IP stack, but that would lead to slow performance of 20 to 50 microseconds. So the reason I'm showing you this is because I want you to know about this latency, that if you were to use it using the standard TCP IP stack, this is what you would incur, okay? But there you go. I think if you know me, you know that I'm terrible at networking. This is a little bit of a networking course, and so I want to uplift a very simple term because I keep forgetting what it is. If you obviously are networking, this is going to be very simple, but if you're not, it's worth a review. What is a network fabric? So it is a high-performance, unified, and automated network architecture that interweaves hardware, such as switches, routers, cables, and software in a single cohesive mesh. An example here would be, let's say, NDR InfiniBand at 400 gigabytes per port with 400 gigabytes Ethernet with ROC version 2. So we're seeing all these accumulative terms. NDR, InfiniBand, ROC, which is obviously using RDMA. You can see we have 4 fabric switches. Okay, and it's going to a 48 top rack of switches down here below. If we want to anchor that a bit better into our use case, imagine you have a compute InfiniBand fabric for a full node of 127 nodes. I feel like it's supposed to be 128. Why is it 127? I don't know. But anyway, we'll say 127 nodes. It's probably 128. And here you can see that fabric, right? And so what is it using? Well, if you look down below here, you can see NDR in red, NDR in here, and NDR in this one. And so it's obviously using InfiniBand, NDR with RDMA, right? And you can see them networked together. And that's the best I can explain it. But there you go. NVIDIA Magnum I/O is an input-output subsystem for data centers. It's an abstraction layer to various NVIDIA technologies, bypassing the CPU for improved performance. So look at that right diagram where you see CUDA X, CUDA, and on the top there, different types of graphics cards. So, well, not necessarily, but RTX, Rapids, AI, a variety of things we need to interface with. And then down below, we have Magnum I/O with storage I/O, network I/O, in-network compute, and I/O management. So let's just take a look at some of the things they have. For storage I/O, this is where you're going to get GPU direct storage, where you can access that. You have your NVMe Snap. For network I/O, NVIDIA NVLink, InfiniBand, Ethernet networks, GPU Direct RDMA, the NCCL. These are all things that we've covered in this course. So just pointing out the ones that you should know. In-network compute, so Bluefield DPUs, which we have covered. And that's it. And so, just remember that it's a abstraction layer. And if you can remember some of those key things that it does, if you do get a question on NVIDIA Magnum, then there you go. Okay. Let's take a look here at NVIDIA desktop density. And before we do, we need to describe what is a VDI. So VDI stands for Virtual Desktop Infrastructure, and it is, and I know there's a double is there, I apologize, you know me, always making mistakes, is a technology that hosts users' desktop environments, such as operating systems, apps, and data, on central, secure servers in a data center. NVIDIA vGPUs are logical divisions of a GPU compute, which can power your VDI. So it's very important that we understand what vGPUs are. And so NVIDIA defines desktop density. And I had to do this because desktop density means more than one thing, but in NVIDIA's terms, this is what it means, is that it's high-performance AI personal workstation, so small, form factor, massive compute. And it's also about being a VDI in a data center with high user density per GPU. So NVIDIA vGPU software enables a single data center GPU to support up to 32 desktops. So that is 32 VDUs concurrently on a single GPU. Notice, okay, that I've highlighted 32 virtual desktops. If you get a question on an NVIDIA desktop density and they're asking you, how much does it up to support to? It's 32. There you go. All right, let's take a look here at Gigabit Ethernet. This is a networking standard that transmits data in 1 gigabits per second. And so when we're talking about AI clusters, we're looking at the 100 gigabit Ethernet to 1.6 terabyte Ethernet, which again still is emerging at this point. And so you might see questions talking about throughput and these speeds, and that's all well and good. But the thing you have to factor in is, remember, regardless of throughput, you need to factor in latency. So for GPU to GPU communication, the fewer steps it has, the lower latency it's going to be, because obviously it's going through there. If it has to go some other route, you have to factor in latency. And even with InfiniBand, there is latency. And we know that at the very least, if we bring up the adapter latency, that even SDR, the oldest version of InfiniBand, has 5 microseconds of latency, right? But with NDR, and look down at NDR, it says HDR is under a microsecond. So there you can see 0.6, and NDR doesn't tell us. But if we want to just, be realistic with our time, we could say 1 to 2 microseconds, but it shows in the adapter latency that NDR is very, 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 very low, right? So I'm saying 1 to 2 down below, but it's saying on paper that it's even lower than that. And so, if you get a question and it's talking about throughput, factor in the latency and factor in the latency that you have to have, even with InfiniBand, with direct GPU to GPU stuff, or consider if it's not that, that there's going to be greater latency going through the CPU or other means, okay? So during the exam, I came up with a term I did not know, which was PUE. I don't build data centers, but so maybe those that are networking data centers are going to know what this is, but I didn't, so I'm including in the course. So PUE stands for Power Usage effectiveness, or power unit efficiency, is a ratio that describes how efficiently a computer data center uses energy, and specifically how much energy is used by the computing equipment. So here you have PUE with total facility power with IT equipment power underneath. So an ideal PUE is 1.0. Anything that isn't considered a computing device in a data center falls in the category of facility energy consumption. So while modern, highly efficient data centers may achieve a ratio of 1.2 or less, the industry average often hovers around 1.58 and 1.8. That's great that it's like 1 is ideal and like nobody is near it. But that's interesting. There you go. All right, so another term that I came across that I wasn't familiar with, and we're going to cover, is the single instruction multi-thread. So the SMIT, I don't know how you'd say that, but SIMT, and it is an execution model used in parallel computing where a single central control unit, and I'm going to get my pen tool out here so we can look at it. So the control unit here, or CUs, broadcast instructions to multiple processing units, which it says PEs here, but I believe that it's actually, these are the PUs here, for them to all optionally perform simultaneous, synchronous, and fully independent parallel execution of one instruction. Okay? And so it's because I came across terms of CUs and PUs, and, so now we know what CUs and PUs are in relation to each other, and it's part of this single instruction multi-thread execution model, okay? All right, let's talk about out-of-memory error. So out-of-memory error is exactly what it means, is when your system is using up all the memory and halts the system operation. And this is something that can happen when we're working with LLMs, specifically when we are trying to train them. So imagine we have H100 and we're training a 70 billion parameter LLM. And we have a cluster of 8 H100s using mixed precision of FP16, and each has 80 gigabytes of memory, so 640 in total, and the model weights is only 140 gigabytes. So you think, okay, I have well over the amount to hold that model memory, but I've told you earlier that when you're training, you need more memory than running the model weights for when you have inference. It could be 2, it could be 4 times, and it could even be more. It really depends on the precision and to what level you are training. I often say 2 to 4 times, but in this particular scenario, you could have 12 to 16 times the model weights for FP16 for full parameter training. So you might say, oh, I do 4 times 140, I had 560, and so I'm fine. But the honest truth is that you could still run into it because now we're running FP16. So I was trying to present you a trick because I keep telling you in this course 2 to 4 times, 2 to 4 times. But, it really comes down to it depends. It depends on those parameters. Just know that if you get out of memory, it's because you don't have enough memory, and you have to consider those factors there, okay? This one looks a lot like out of memory, but this is out of bounds network. So an out of bounds network is a dedicated, secure, or physically logically separated infrastructure used to manage, monitor, and troubleshoot critical network devices independently of the main production network. Sounds useful, right? It provides a failover path for remote administrators, allowing access during network outages or device failures. So with GPU infrastructure, you can have an out-of-bound network in the case the GPU infrastructure fails, but you need a means to manage, monitor, and troubleshoot said infrastructure. Because, consider you're running real hot machines. They get real hot, require a lot of electricity. They can run out of memory. They just can get stalled. There's so many things that can go wrong with them. So having an out-of-bound network that you can then troubleshoot it is a great idea so that, the thing that you're using to troubleshoot it isn't stalled itself, okay? All right, let's take a look at homomorphic encryption, or HE, lets users to perform computations on encrypted data. So when you don't trust the computation servers with your data, you can use HE to mitigate risk. So the idea here is that you encrypt your data, so whatever that is, right? And the encrypted data is then processed with whatever information, but the results are still encrypted, okay? So only you decrypt the final answer. And so this is really good when you want to use data center servers that aren't your own for computation, but without leaks of information. And you can have different levels of HE. So you have partially HE, somewhat HE, which is called SHE, I don't know why, and fully HE. And so obviously with full or fully HE, it's unlimited additions and multiplications. So you can do as much as you want with the data. This is obviously the most ideal, but we're covering this because we're going to be covering something that has FHE. And so that's why we're talking about it, so you know this term, okay? So ARC3EX, I have no idea how you're supposed to pronounce that, but the accelerated encryption execution is an end-to-end framework that enables you to specify algorithms in C++ using standard data types and automatically convert this algorithm into a FHE. That's why we were talking about homomorphic encryption earlier, and the representation that can be launched on arbitrary numbers of GPUs for efficient evaluation. So if you get a question on your exam, it's talking about, hey, your team doesn't trust the data center. How can they, use it without having fear of using it? It's going to come down to using homomorphic encryption, or look for FHE. And specifically what NVIDIA systems use is this ARC tier EX, okay? So it could be under that name. They could be saying FHE. But if you remember that case, then you will know what the answer is from a security perspective, okay? Let's take a look here at NVIDIA GPU Cloud, or NGC, is the portal for enterprise services, software management tools, and support for end-to-end AI and digital twin workflows, which you can find on the catalog at catalog.ngc.nvidia.com. So the NGC catalog is the repo of GPU-optimized containers, models, and scripts updated monthly for AI development. Could you use this stuff locally? I don't know. I mean, we might have been using it earlier, because if you see down below, we have NVIDIA Trident Inference Server. And I wasn't paying attention to where that URL was coming from, but I have a feeling that we probably have been referencing these containers prior. So probably using the Docker command, we're probably referencing stuff that's coming from here. But yeah, that's probably what it is. But anyway, it's a good place to look and see what we can utilize. But there you go. Just know what NGC is, okay? And specifically the catalog, where all this stuff is coming from. All right, let's take a look here at NVIDIA GPU Direct. And so it is a family of technologies that allow you to read and write directly to the GPU. So you have GPU Direct Storage, GPU Direct Remote Directory, Remote Direct Memory Access, so RDMA. You have peer-to-peer and video. We're not going to be interested in the last two on the end, but we will be interested in covering GPU Direct RDMA and possibly storage. So again, you just need to know that it's a family of stuff. And then we'll actually go jump in and take a look at NVIDIA GPU Direct RDM, which we absolutely want to know, okay? All right, so we are taking a look here at NVIDIA GPU Direct RDMA, so Remote Direct Memory Access, which allows for direct communication between GPUs, completely bypassing the CPU for 10 times performance. We talked about RDMA earlier, as this was where you need specialized hardware that supports it and has the software to do it. And so this is RDMA, but it's GPU Direct. So it's like NVIDIA's flavor of it for their hardware. And so GPU Direct RDMA provides GPU to GPU communication across nodes. So imagine here we have our network. Notice that we have GPUs on the far side of each one, and they're using ConnectX. And through ConnectX, we're going to be using InfiniBand with RDMA to have a super fast connection. And so this is the line that we're looking at. And you notice that it is completely skipping over the CPUs and the CPU memory because we're doing GPU to GPU. So RDMA was introduced in the Kepler class GPUs of CUDA 5 in 2012, so it's been around for a long time. GPU Direct RDMA fully supports InfiniBand NDR, so 500 gigabits per second. And just remember that, there's different cables and different speeds, different cables. There's 200, and there's 400. And so this one for GPU Direct RDMA supports 400. And remember, H100s, I believe, can support NDR 400s, right? If you have the not as good cables, then they're not going to go as fast. GPU Direct RDMA isn't limited by InfiniBand generations. So, that's good because it sounds like if there are new generations coming out that, we could have more options down the road. It's limited by GPU NIC platform support. Okay, so it's a combination of things that tell you the limitation. Okay, so RDMA over coverage Ethernet. So ROC works with RDMA. As you can see, it's right there in the name. We've covered that elsewhere after RDMA. Regardless of throughput, you can have latency depending on your path. GPU to GPU with InfiniBand NDR will get you 1 to 2 microseconds latency. If you have to communicate through CPUs, you can see that there's probably 10 to 30 microseconds. So I keep repeating this, right? And I know that the graph says that it's under a microsecond, but for your exam, just pad that time. And so InfiniBand NDR, factor in 1 to 2 microseconds of latency. And if it's not going through that and it's going through the CPU, add 30 seconds microsecond latency. And that will help you with any of those little trick questions if they happen to appear for you, okay? All right, so NVIDIA Rapids is a data science framework and is a collection of libraries for running end-to-end data science pipelines completely on the GPU. So we have Rapids API, the Rapids libraries, the Rapids projects, and there's a lot in here, but the one that you're going to know is this one here, CUDF, okay? Because I believe that is the one that is giving us data frame. So we see DF for data frame, and so that gives us that compatible data frame that looks a lot like Pandas use. And so that's pretty much the one you really, really want to know here. In terms of all this other stuff is great, but this is the one that we basically need to know. And you just have to understand that's coming from Rapids, okay? So there you go. Let us take a look here at NVIDIA GPU Direct Storage, which enables a direct data path for direct memory access. So DMA transfers between GPU memory and storage, which avoids a bounce buffer through the CPU. Okay, so without GPU Direct Storage, you can experience a significant idle time during data loading phases. And if you have GPU Direct Store enabled and your CPU usage is spiking during loading phases, then enable Rapids CUDA data frame. That's why we were talking about CUDF and the Rapids prior, and we talked about it way earlier in the course, is because we need to know for here. Or you might need to increase. It says increase, double increase. We'll say increase the data load worker processes to parallelize the use of CPUs. So the GPU, GPU Direct Storage Rapids Q file library enables applications and frameworks to leverage GDS technology to increase bandwidth and achieve lower latency. And if you still don't know what the data frame is, do not worry. We are covering it in the next video. All right, so here we are with QDF, which apparently is pronounced CoDF, but I'm not going to do that. I really like that NVIDIA takes the time to tell us, but I just don't care. But it is a Python GPU data frame library built on the Apache Arrow columnar memory format for loading, joining, aggregating, filtering, and otherwise manipulating data. So over here, you can see that we are utilizing it. And so we're reading the Parquet file and we're performing operations. If you were to compare that to Pandas, you'll notice that it's literally the exact same commands, right? So it's very Panda friendly. So more or less, you basically just swap out the import statement and the variable, and you are good to go. Let's Let us take a look here at the NVIDIA NeMo framework. Is a development platform for building custom generative AI models. And this framework supports large language models, computer vision, ASR, natural language processing, text-to-speech. And NeMo lets you build, monitor, optimize AI agents. It's a complete lifecycle management for your AI tools. So basically, it does everything. I'm trying to remember what the other open source one is, but like when you think of AWS SageMaker, think of NeMo framework. If you think of Azure Machine Learning Studio or whatever it's called, think of this. If you think of Vertex AI, think of this as the equivalent where you have this end-to-end thing that you can utilize, but it's an NVIDIA thing, okay? We are taking a look at NVIDIA MIG. We've mentioned this a few times, but we'll mention it again. So NVIDIA multi-instance GPUs is a technology that allows a GPU to be divided into multiple fully isolated independent instances acting as separate GPU devices. And so MIG can be used starting with the NVIDIA Ampere generation, I don't know how to pronounce that, with an 8.0 compute capacity. So that's going to support Blackwell, Hopper, and Ampere. You can see over here, based on what product you are utilizing, right? It's going to tell you how many of the max instances that you can have, like that you can split it into, okay? So it's going to really vary on very specific each piece of hardware you have. The compute capacity in NVIDIA's versioning system for GPU architectures, that's what that is, which I know we covered this somewhere else in another video, so we've already covered that, but we're just repeating again that compute capability is NVIDIA's versioning for systems for GPU architectures. And the MIG is physically partitioning the GPU into separate instances, each with dedicated SMs, L2 cache slices, and memory controllers. So that is how we're cutting it up, okay? But what you need to remember is MIG is for taking a GPU and creating a bunch of vGPUs, and there's a limit based on what you're utilizing, okay? Let us take a look here at Onyx, which is an open neural network exchange, and it's an open source framework agnostic model format that can be exported from most major frameworks. Onyx provides a common language any machine learning framework can use to describe its models. So imagine you need a linear regression. Onyx contains all the math functions necessary for ML models to implement its inference function. So by sticking with Onyx, we're normalizing all these function calls so that we can move from one thing to another, okay? So ML models implemented with the Onyx framework is often referenced as Onyx graphs, okay? And that's kind of a visualization of it. Onyx does have an entire ecosystem of tools to help build frameworks and converters, deploy, optimize, visualize Onyx. And there's more than just these, but like the ones that I thought were really useful are the optimizers and the visualizers. One in particular that's kind of fun is Netron, where you can go here and load in an Onyx model, and it'll completely give you the graph. And it supports quite a few things. It's not the only visualizer, but it's one of the cooler ones. You can use in your browser. You can install it locally. There's no cost to it, so it's pretty darn cool. And it does support more models than what model formats on the left-hand side, but Onyx is what we want to use it for, okay? So TensorRT for RTX is an inference library that allows optimized and easy deployment of AI models for the RTX GPUs, which I have, which is great. And TensorRT RTX ensures that your AI workloads never steal performance from graphics, which that's a challenge that we have. I'm running OBS, and so that might be something that I'm fighting with all the time. A drop-in replacement for the NVIDIA TensorRT in applications targeting NVIDIA RTX GPUs from Turing all the way to the Blackwell generations. TensorRT introduces just-in-time optimizer. TensorRT for RTX is compact under 200 megabytes. And TensorRT for RTX optimizes CNN, diffusion, and speech models expressed in Onyx or native C++ APIs for running on NVIDIA RTX GPUs. Unlike NVIDIA TensorRT library inference library, this library does not support other NVIDIA GPU platforms like data center, edge, and embedded. The reason I'm covering this is because when you're looking at TensorRT, it can get really confusing because the wording is very similar. And so, I mean, of course, there's a benefit to me to know this because I have an RTX graphics card, but just to not get confused by the terms and for you to know that RTX is a professional workstation, okay, not for data centers. let's take a look here at TensorRT. So it is an ecosystem of APIs for high-performance deep learning inference. Okay, that's all what it is. And TensorRT optimizes the model for target hardware, such as NVIDIA GPUs. So now we know what it is. I didn't cover it in the last slide, but we're covering it now. Let's talk about TensorRT LLMs. This allows you to serve LLM models using TensorRT engine, using Python code. And so an example would be, we have a checkpoint here for TensorRT and the LLM checkpoint format. So we are doing a conversion to prepare it. Then we are building our engine, and then we're running inference. So this is just kind of an example of taking that code and bringing it over to TensorRT LLMs. So it's not super exciting here. But yeah, and it's using the Gemma model, but yeah, there's not much to say. I mean, if we go put it into action, it might be more interesting. Before the exam itself, it's not gonna be that exciting, okay? So let's talk about TensorRT LM quantization. So quantization reduces the memory footprint and computational costs by converting models' weights to a lower precision. So let's say BF16 to F8, and TensorRT-LM has quantization recipes for FP4, FP8, and a bunch of other ones. A quant method is made of 3 parts: weight precision formats, activation precision algorithms. An H100's transformer engine is purpose-built for FP8 inference. Okay, so Llama 70 billion would be a quant of FP8 format for optimal running. So maybe you might want to do quantization of something to FP8. Now, I believe that we said when we looked at the transfer engine, it can run FP8 or FP16, but FP8 is probably what you want to run. So if you know that you can use TensorRT LLM through quantization to bring it to the precision that's going to be best performant for it, that's what you're going to want to do. Okay, and on the exam, they might throw to you some of these quantization terms or numbers, but just remember the underlying thing, which is we want to run FP8 on an H100. We're using quantization to bring it down to that format. Okay. I know we talked about NCCL early in the course, but because this part's a little bit heavier, I left the best part for last because I want you to go into your exam with this information as fresh as possible, because I felt that these questions here, talking about collective operations, were the finickiest, right? And so that's why I've put this at the tail end of the course. So NCCL, collective operations, has the following collective communication primitives. And so we have all reduce, broadcast, reduce, all gather, reduce, scatter, all to all, gather, and scatter. So what is a rank? It is a unique identifier assigned to each process that's in distributed computation. So each GPU gets its own unique ID when we perform a distributed operation. If you remember what NCCL does, it allows you to do things over the network, distributed across GPUs. So you have GPU to GPU communication, but this is for over Ethernet or over to another rack, right? So when performing collective operations like all reduce, broadcast, gather, every single rank must call the same operation with the matching parameters, right? So if you have rank 0, 1, 2, 3, look, they're all doing all reduce, they're all doing 1,000, they're all doing float 32. Rank is just the number to identify that unique GPU. You might use all reduce to perform a gradient for your neural network. So that might be a case where you might use it. You might hear those terms on the exam where they're talking about, like, should you use an all reduce? And they're doing a gradient and stuff like that, okay? So let's talk about all these collective operations. So all reduce reduces operations and performs reductions on data. So the example of this is a sum, a min, a max. We're reducing a bunch of stuff to a single thing, like summing something up. So you have the all reduce. This is going to reduces the store, the same result in all ranks. So look at the graphic on the left-hand side. I'll get my pen tool out, right? So here we have our incoming values, reduces the stores, and the same result in all ranks. So the same value is going to go in all 4 of these. So whatever it is, so if it's going to sum it out, the sum is going to get returned back to all those GPUs. Okay, remember, ranks are just GPUs. They got an input, they're doing an output. So here, reduce stores the results only in the receive buffer. So very similar. So we're doing a sum, but we're only sending it back to a single machine, right? Or single GPU. And so here we have reduce scatter. So reduce scatter. So the result is scattered in equal sized blocks between ranks, each rank getting a chunk of the data based on the rank index impacted by a different rank by device mapping. Okay, so that kind of makes sense. We have broadcast. The broadcast operation copies the n element buffer from the root rank to all ranks. So you're saying, okay, this GPU, give its value and send it over to all the other ones, right? We have all gather operation. Gathers n values from k ranks into an output buffer of size kn. It distributes that result of ranks. The output is ordered by rank index. The all gather operation is therefore impacted by different ranks of the device mapping. So you can see the values, how they're going to be stacked in here as such. So there you go. We have all to all. Okay, so all to all is going to do an all-to-all operation between k ranks. Each rank provides an input buffer of size kn values where the nth chunk of n values is sent to the destination rank. Each rank receives an output value where the chunks of n values come to the source of I rank. I know some of these things are confusing, but like if you understand reduce all, like or these other ones, you're going to be fine. These ones here, they're a little bit too complicated, but I just want you to know them. Okay, so don't stress out about it. The gather, like it says the word gather, it's going to gather them all together, right? So see the graphic left-hand side, right side, we're gathering them all together. Scatter, it's going to scatter them. Right? So we have, and the last one here, hold on a second. This is the same one. Yep, and I have a repeat here. So anyway, that's all your operations. So scatter, we have our gather, we have all to all, we have our all gather, we have our broadcast, which is pretty straightforward, and our all reduce. And I feel like most questions are going to be hitting you with the all reduce. So if you understand all reduce, you'll probably be really, really good. But there you go.